The History of Mercury, the smallest and most hidden planet. Mercury is the first of our series of documentaries dedicated to the planets of the solar system, comprehensively describing their history and characteristics. It's the innermost planet of our solar system, so close to the Sun that it's almost always hidden in its blinding glare. We won't limit ourselves to describing the most well-known characteristics of this small planet. We'll go beyond, exploring its peculiar orbit that confirmed Einstein's theory of relativity, its strange relationship between day and year, its crater-riddled surface, and the surprising discoveries that continue to amaze astronomers. Comprehensive means exactly this: a detailed account, rich with information and insights that will lead you to see Mercury with new eyes, appreciating its complexity and hidden charm. Mercury is a planet of contrasts and mysteries. The first world of our solar system, so close to the Sun yet capable of hosting ice in its polar craters. So small it almost seems like a moon, yet so dense it harbors a disproportionately large metallic core. So slow in its rotation that a Mercurian day lasts 2 of its years, yet so quick in its orbit that it completes a full circuit around the Sun in just 88 Earth days. Its surface, marked by countless craters, is an open book on the evolution of the solar system, a cosmic archive etched in rock just waiting to be deciphered. But let's proceed in order and get to know this planet better through its numbers. With a diameter of just 4,879 kilometers or 3,032 miles, about 38.3% of Earth's, Mercury is the smallest planet in the solar system since Pluto was reclassified as a dwarf planet. Its mass is approximately 5.5% of Earth's, but despite its small size, its density is surprisingly high, 5.43 grams per cubic centimeter, or 338.4 pounds per cubic foot. Second only to our planet, suggesting a metallic core that occupies a full 60% of its total volume. Mercury orbits the Sun at an average distance of 57.9 million kilometers, or 36 million miles, 0.39 astronomical units, completing a revolution in 88 Earth days. Its orbit is the most eccentric of all planets, with a value of 0.21 that varies its distance from the Sun from a minimum of 46 million kilometers, or 28.6 million miles, to a maximum of 70 million kilometers, or 43.5 million miles. The planet rotates on its axis in 58.6 Earth days, with an axial tilt of just 0.03 degrees, practically perpendicular to the orbital plane. The temperature on the surface varies dramatically from a scorching 427 degrees Celsius or 800 degrees Fahrenheit at the equator during the day to a frigid minus 173 degrees Celsius or minus 280 degrees Fahrenheit during the polar night, the most extreme temperature range in the entire solar system. The surface gravity is 0.38 times that of Earth. If you weigh 154 pounds on Earth, you would weigh just 58.5 pounds on Mercury. This cold, objective data doesn't tell the true story of this small, rocky world. However, its biography is literally written on its skin. Lacking a significant protective atmosphere and geological processes that continuously renew its surface, Mercury preserves, like scars, the traces of every cosmic encounter in its long existence. And the craters that dot its surface are testimony to a series of violent impacts that occurred about 3.9 billion years ago in a period known as the Late Heavy Bombardment. It's not easy to investigate the early phases of Mercury's life because it's the most hidden planet in the solar system. Studying it thoroughly, as we'll discuss later, is a challenge even with space-age technology. In the era when astronomers can only observe it with Earth-based telescopes, getting information about Mercury was almost impossible due to its position, being the innermost planet of the solar system. To see it from Earth, we're forced to look towards the Sun. Hidden in the Sun's glare like a frightened child, Mercury is difficult to see in the blinding light of our star and peeks out only occasionally for short periods. From our position, we see Mercury moving from one side of the Sun to the other as it orbits. For about a month, the planet is visible as an evening star at twilight, low on the horizon after sunset. For another month, it disappears in the Sun's glare. Then it becomes a morning star, visible before dawn for the next month. After that, it disappears for another month behind the Sun and finally returns to its initial position. It takes 116 days to complete this cycle. Initially, ancient Greek astronomers believed that Mercury's evening and morning appearances belonged to two different planets, which they called Apollo and Hermes. It seems the mathematician Pythagoras, around 500 BCE, realized that the two planets were actually one. He probably noticed they had a similar appearance, moved at the same speed, and crucially, whenever Apollo became visible, Hermes disappeared and vice versa. The name Hermes was the one that prevailed, so much so that even today in Greece the planet is called that. Elsewhere, the name Mercury spread, which was the Roman equivalent of the Greek god Hermes. Like all planets, Mercury follows an elliptical orbit around the Sun, which occupies one of the two foci of the ellipse. This geometry, so different from the perfect circle imagined by astronomers before Johannes Kepler, implies that the distance between the planet and our star varies continuously during its revolution. Like a pendulum that accelerates at the lowest point of its oscillation, Mercury also modifies its speed, faster when close to the Sun, slower when farther away. The parameter that measures this variation is called the eccentricity of the ellipse, and it's a number that ranges from 0 in the case of no variation, that is, if the orbit is in fact a perfect circle, to almost 1 if the ellipse has a long, narrow shape. The eccentricity of Earth's orbit, for example, is 0.017, almost circular. Mercury's eccentricity, however, is 0.2056, making it the planet with the most eccentric orbit of all. This means that its distance from the Sun is extremely variable, ranging from 46 to 70 million kilometers, or from about 1/3 to almost half the distance between Earth and the Sun. Early studies. First hypotheses. Due to the difficulties of observation, even in the telescopic era, Mercury remained for a long time a little studied planet. The first attempt to map its surface was toward the end of the 19th century. The Italian astronomer Giovanni Virginio Schiaparelli, the same one who observed the canals on Mars, who was also the first to hypothesize that Mercury's rotation period was equal to its revolution period, just under 88 Earth days. The work of mapping the planet was then continued and expanded by the Greek astronomer Eugene Michel Antonati, who in 1934 published the first detailed maps of its surface features. But to begin an in-depth understanding of the planet's morphology and internal structure, we had to wait until the second half of the last century, first with Earth-based radio and optical observations, then with space missions. The first important discovery was that, contrary to what Schiaparelli had initially proposed, the rotation period is not synchronous with the revolution period, but that the two are in 3:2 ratio. In other words, this means that the planet rotates on its axis 3 times for every 2 orbits around the Sun. The experimental data from the early 1960s provided by both Soviet and American radio observations was indeed about 59 days for the rotation period, compared to almost 88 for the revolution period. It was the Italian astronomer Giuseppe Bepi-Colombo who suggested that a 3:2 resonance between the two periods relative to the Sun was a stable solution, despite the astonishment of much of the astronomical community, convinced that the 1-to-1 resonance, synchrony between the two motions as observed for our Moon, was the more likely scenario. At the origin of this phenomena is the force of gravity that is exerted reciprocally between the celestial bodies involved, and in particular the tidal forces, which act differently between the different parts of the same body. For example, for Mercury, the greater attraction by the Sun of the hemisphere facing the star versus the lesser attraction felt by the opposite hemisphere. This action is always dissipative and slows down the rotation motion until it reaches an equilibrium solution, such as the 1-to-1 resonance for the Moon relative to Earth, or the 3-to-2 resonance of Mercury relative to the Sun. But be careful, all of this is not without consequences for the day-night cycle of the small planet. In practice, because of this very particular relationship between the rotation period and the revolution period, combined with the high eccentricity of the orbit, a potential Mercurian inhabitant would have to wait 176 days before seeing the Sun return to the same position in the sky. During the course of a Mercurian day, they would see the Sun rise in the east and advance very slowly across the sky, about 3 times slower than the sidereal motion of stars, increasingly growing in apparent diameter. Near the meridian, the Sun would slow down even more until it stopped completely. Then the Sun would perform a double reversal of motion before resuming its journey toward the western horizon, which it would reach 88 days later, returning to its original dimensions. Other observers, located at points with a different longitude, would see different but equally bizarre movements. At midday from certain longitudes, the Sun may appear 3 times as large as it does from Earth, and it is 7 times brighter. Nevertheless, the surrounding sky is black and star-speckled inasmuch as Mercury does not have an atmosphere in the traditional sense. It is a lonely sky without a satellite, nor even rings orbiting the planet. The surface. Are we on the Moon? Mercury's surface appearance, well studied only following dedicated space explorations, is not very dissimilar from that of the Moon, alternating between regions rich in craters and smoother, flatter areas that suggest past volcanic activity, like the one that gave rise to the lunar seas. On the other hand, the lack of an atmosphere causes the absence of erosive processes and surface features that can be preserved for billions of years. The structures that dominate Mercury's surface are impact craters. As on all other celestial bodies in the solar system with a solid crust, craters are of all sizes, and their topography depends on their diameter. Below 10 kilometers or 6.2 miles, there are only simple bowl-shaped craters. Between 10 and 130 kilometers or 6.2 and 80.8 miles, craters have a central peak. Between 130 and 310 kilometers or 80.8 and 192.6 miles, in addition to the peak, a central ring also appears, while beyond 310 kilometers in diameter, multiple rings appear. At equal diameter, Mercury's craters have an ejecta blanket that is 0.65 times smaller than that of lunar craters, probably an effect of the greater acceleration of gravity compared to the Moon. And then there are the smooth plains, which are the equivalent of the lunar Maria. About 40% of the hemisphere photographed by Mariner 10 is occupied by these plains, in 90% of cases associated with impact basins. From the analysis of the number of craters superimposed on the smooth plains, it can be deduced that these must have formed at the end of the primordial bombardment period, and their origin is probably volcanic. The intercrater plains, that is, those included between the craters, are more difficult to interpret than the smooth ones. On the lunar highlands, craters are so densely packed that they overlap each other. This is the phenomena of crater saturation. On Mercury, large portions of cratered surface are not saturated, and between one crater and another there is relatively flat terrain. Compared to the lunar highlands, craters with a diameter below 40 kilometers are scarcer in Mercury's plains. The distribution of intercrater plains and the lack of impact basins of which they could constitute the ejecta argue in favor of their volcanic origin. Another peculiar feature of Mercury's surface are the lobate scarps. These are abrupt crustal fractures ranging from 20 to 500 kilometers, or 12.4 to 310.7 miles in length, with heights between 100 and 3,000 meters, or 328 to 9,843 feet. The most notable of these structures is Discovery Rupes. In Latin, scarp is called rupes. There are few craters superimposed on the scarps, which therefore must have formed relatively late in the planet's history. In any case, only after the formation of the intercrater plains and the larger basins. The most plausible explanation for the formation of this system of fractures is that it is the result of the contraction of the planet's crust due to cooling. They would therefore be compression faults. A decrease in the planet's radius of just 2 kilometers or 1.2 miles is sufficient to account for the system of fractures that is observed. Nothing similar exists on the other terrestrial planets. In addition to the scarps, other elongated structures, the troughs, are also present on Mercury's surface. Troughs are structures a few hundred meters or several hundred feet deep, about 10 kilometers or 6.2 miles wide, and more than 100 kilometers or 62 miles long. Unlike scarps, troughs are aligned in 3 preferential directions: northeast, northwest, and north-south. The troughs form what is called Mercury's grid. Similar structures are also observed on the Moon and are attributed to the slowing of the planet's rotation period due to solar tides. Among the records cited earlier, Mercury also holds that of having one of the largest craters in the solar system in relation to the size of the planet that hosts it. The Caloris Basin, or Caloris Planitia, an impact crater almost 1,600 kilometers or 995 miles in diameter. Like the large lunar craters, Caloris Planitia is a lava plain and is surrounded by a ring of mountains up to 2,000 meters or 6,562 feet high. It is located at Mercury's equator, the hottest area of the planet, where the sun's rays are strongest. Not coincidentally, its name means plain of heat. Caloris Planitia was created by the impact of an asteroid about 100 kilometers or 62 miles in diameter, probably 10 times larger than the asteroid that caused the extinction of the dinosaurs on Earth. The impact was so violent, as evidenced by the crater walls, raised almost 2 kilometers or 1.2 miles above the surrounding terrain, that the effects propagated throughout the planet, generating seismic waves that traversed the entire planet, causing earthquakes at the diametrically opposite point, where a vast area called weird terrain formed. This region, characterized by a series of irregular hills and small craters with a conformation different from any other observed on the planet, was probably generated by the meeting of seismic waves that propagated on the planet following the impact, eventually breaking up and raising the previous terrain, although some hypothesize that it is made up of materials that fell back onto the planet's surface once they were lifted by the collision. Then the seismic waves returned, and the roar of the earthquake filled the planet, making it vibrate like a tuning fork for hours or perhaps days. The vibrations cracked Mercury's surface, from which incandescent lava began to emerge. Volcanic activity affected large areas, which were invaded by lava flows and transformed into smooth plains, the exact opposite of the chaotic terrain. The mountains trembled, landslides fell from their sides. The consequences of the impact extended to the entire planet. The formation of Caloris Planitia was a terrible event with global effects. The impact of the asteroid profoundly disrupted Mercury. If it had been larger, it would have literally torn the planet to pieces. The internal structure, the core, the magnetosphere, truly torn to pieces? Well, perhaps not. Mercury is in fact the planet with the highest density of iron, and it would therefore not be easy to reduce it to shreds. Nearly 3/4 of its diameter is occupied by a large ferrous core, 3,600 kilometers or 2,237 miles, compared to a total diameter of almost 4,900 kilometers or 3,032 miles. This core would occupy 40% of the planet's volume and would constitute a full 70% of its mass. In comparison, Earth's core is only 17% of our planet's volume. Proportionally, Mercury has the largest iron core of all the terrestrial planets. It's not easy to understand why, especially since theoretical models on the birth of the solar system predict lower densities. It's possible that the Sun, at the beginning of its existence, swept the innermost part of the solar nebula more energetically than predicted, allowing only heavy metals to aggregate. An alternative is the impact of Mercury with a large asteroid capable of removing the outer mantle while leaving the iron core intact. In this scenario, the impact would have occurred after the planet's differentiation. The rest of the planet is composed of a mantle and a crust made of materials similar to those of Earth's crust, especially silicon-based. Despite many thinking that Mercury's rotation was too slow for it to develop a magnetic field, the planet actually has one, dipolar and global, generated by a dynamo effect similar to that of Earth, due to the rotation of the planet's large liquid core. Although faint, its intensity is about 1% of Earth's. It is still intense enough to produce a magnetosphere and thus deflect much of the incoming solar wind. And the atmosphere? The planet's atmosphere, composed of hydrogen, helium, sodium, potassium, and calcium, is extremely rarefied and therefore does not contain enough gas to reduce the heat and light it receives from the sun. Moreover, the slow rotation of the planet exposes different areas of the surface to direct sunlight for long periods. This leads to the highest temperature range among all the planets in the solar system. As we've already mentioned, Mercury's distance from the Sun is highly variable, so the amount of light and heat reaching the planet can become at times more than double or less than half. Thus, the temperature also changes enormously depending on the time of day and the latitude considered. During the day, the surface temperature ranges from -183 degrees Celsius at the poles to 427 degrees Celsius at the equator. At night, heat disperses quickly from the bare rocks, and the surface temperature can drop to -200 degrees Celsius. At Mercury's equator, common metals like lead and tin would melt, and the plastic of a potential lander would end up melting or decomposing. Obviously, all this would be fatal for electronic instrumentation, with plastic-coated components, metal cables, and solders, unless adequate measures were taken to address the problem. So far, however, no one has found a practical solution. Mercury confirms general relativity. It's impossible to talk about Mercury without mentioning the fundamental contribution of this planet to the confirmation of the theory of general relativity. Observations show that every time it completes a circuit around the Sun, its elliptical orbit rotates in space, advancing the perihelion, that is, the point of maximum approach to the Sun. As we well know, Newton's theory of gravitation is extraordinarily precise in describing planetary orbits and the position of planets along their path. In the case of Mercury, however, it was noticed in the 19th century that the measurement becomes mysteriously imprecise. At the end of each circuit around the Sun, the planet was found to be in a position slightly different from that predicted by Newtonian calculations, and after a few decades, the differences accumulated, resulting in a significant deviation. Normally, as happens for all other planets, albeit to a much lesser extent, the major axis of the ellipse slowly rotates around the Sun, which is at one of the foci. This rotation of the orbit is called precession, and it is predicted by Newtonian theory. All planets, in fact, are characterized by this phenomena, caused mainly by the gravitational attraction of other planets and especially that of the Sun. The precession speed can be calculated with Newton's theory of gravitation, which provides an almost exact answer for all planets except Mercury and Venus. During the 19th century, a precession of 5,600 arcseconds, approximately 1.6 degrees per century, was measured for Mercury's orbit. However, calculations based on Newton's theory explained only 5,557 arcseconds per century. What else was missing from the theoretical model to justify those missing 43 seconds? An arcsecond is 1/3600th of a degree, so it's a minimal difference. But it couldn't be ignored, and it had become quite a headache for scientists of the time. Before having a satisfactory explanation, the French astronomer Urbain Le Verrier, the same one who had predicted the existence of Neptune, hypothesized that the anomaly was due to an as-yet unknown planet closer to the Sun than Mercury. This hypothetical planet, named Vulcan, was the object of an astronomical hunt that lasted decades, with alleged observations and denials, until in 1919, Albert Einstein offered an explanation. In his general relativity, gravity is an effect of the curvature of space-time, and a planet's orbit is not a static ellipse but would rotate anyway, even in the absence of the gravitational attraction of other planets. The closer to the Sun, the faster. And when he calculated Mercury's precession using his relativistic model, the German scientist astonished the scientific world by accounting for all 5,600 arcseconds per century. The first space missions, Mariner 10 and Messenger. The proximity to the Sun, even in perspective, has always made the observation and study of this small planet very difficult, which has thus always remained on the margins of general attention, and partly also of scientific attention. For example, there are no photos of Mercury taken by the Hubble Space Telescope, which, to safeguard its sensors, has never pointed its photographic instrumentation in its direction, nor in that of Venus. And only 2 probes have visited Mercury, 3 with the recent Bepi Colombo still operational. It may be the closest of the planets, but it's also terribly difficult to reach. How come? Well, the problem is that heading towards Mercury also means plunging headlong into the Sun's gravitational well, which would attract the spacecraft to itself until it reached such a high speed as to prevent insertion into Mercury's orbit. The spacecraft would need to find a way to slow down, but this would mean carrying enormous amounts of fuel. The only other way is to slow down by relying on numerous gravitational assists with Venus and with Earth itself, with changes of course that, however, inevitably lead to greatly extending the duration of the journey. This explains the scant attention shown to the planet by the various space agencies. The first probe to visit Mercury was NASA's Mariner 10 in the first half of the 1970s, which took only 134 days to reach Mercury. The second was Messenger, with orbital insertion occurring in 2011 after a full 7 years of travel. The enormous disparity in flight times between the two missions depends on the fact that Mariner 10 limited itself to flying over the planet, without trying to orbit around it. It was attracted by the Sun's gravitational field and slowed down only by a flyby with Venus. It had a very rapid encounter with Mercury. Messenger's objective, on the other hand, was to orbit the planet, which it managed to do only after an infinite wandering between Venus and Earth in an attempt to dissipate energy and speed. Mariner 10, launched by NASA on November 3, 1973, to explore Venus and Mercury, was able, thanks to 3 close passes with the planet made between 1974 and 1975, to provide us for the first time with detailed images of its surface, as well as to discover the existence of the planetary magnetic field. Its most important record, however, is that of being the first probe to use the gravitational assist of a planet, Venus, to be directed towards another planet, Mercury. We recall that the slingshot effect consists of exploiting a planet's gravity during a close passage to accelerate or decelerate a probe, or even to modify its trajectory. Depending on the relative position of the orbits and the relative velocities, a probe can thus vary its orbital motion without using its engines, and therefore without consuming fuel, making possible trajectories and objectives otherwise impossible to reach for reasons of cost or time. And finally, 3 incredible facts. In 2008, the Messenger probe, launched in August of 2004, revealed that the planet possesses a long trail of sodium and calcium atoms extending over 2.5 million kilometers, or 1.55 million miles, into space. This phantasmagoric tail, invisible to the human eye but now detectable even with amateur instruments, is generated by the interaction between the solar wind and Mercury's tenuous exosphere. The charged particles of the Sun strike the planet's surface, causing atoms to jump, which are then pushed by the pressure of solar radiation, creating this extraordinary cosmic appendage. Like a planet playing at being a comet, Mercury reminds us that even the seemingly simplest celestial body can hold unexpected wonders. Like this other one we're about to tell you about. Well, believe it or not, despite what common sense tells us, it would be Mercury, not Venus, that is the closest planet to Earth. The relative position of the orbits is always as described in school books, but the distance separating the planets changes if calculated in relation to time. In practice, the orbits of Venus and Earth are separated by a distance of 0.28 astronomical units, while Mercury's orbit is 0.61 AU from Earth's orbit. Put this way, there would seem to be no doubt from a geometric and absolute point of view, Venus is indeed the planet that comes closest to Earth. But if the calculation is made with respect to time, that is, if one counts over a long enough period of time what the average distance of the two planets is, then it is discovered that Mercury spends a longer time in the vicinity of Earth than Venus does, so much so that the average Mercury-Earth distance in the long term is 1.04 AU, while that of Venus is 1.14 AU. It's a bit like what happens to us in everyday life. Between an uncle who comes to visit us once a year and then returns to his home 100 kilometers away, and the neighbor who lives all year round 100 meters from our house, who do you think is, on average, closer to us? Finally, one of the most poetic aspects of Mercury is related to the slowness with which the terminator, the line separating day from night, moves across its surface. Due to Mercury's peculiar rotation, so slow compared to its year, the Terminator advances at a speed of just 3.6 kilometers per hour or 2.2 miles per hour, comparable to that of a person walking at a brisk pace. This means that a hypothetical Mercurian explorer could, in theory, walk along the Terminator, remaining perpetually suspended between the scorching day and the freezing night, in an eternal twilight. Imagine being able to walk along the border between light and darkness, chasing a sunset that lasts for Earth decades, while behind you a dawn drags itself with the same indolence. On Mercury, this is not just a romantic dream, but a direct consequence of its orbital laws, a mathematical poetry written in the language of celestial physics. The story of Venus, a knife hidden among feathers. It's time to turn our gaze towards another fascinating neighbor of Earth, Venus, the planet that has ignited human imagination for millennia. Known as the morning star or the evening star, Venus is a world of contradictions, a place that almost seems like Earth's twin, but hides a hellish face beneath its brilliant surface. In this new chapter of our series, we won't just describe its well-known features, we'll go beyond, exploring its geological history, toxic atmosphere, extreme conditions, and the latest scientific discoveries that continue to astonish astronomers worldwide. Exhaustive truly means that a detailed narrative, rich with information and insights, that will make you see Venus with new eyes, appreciating its complexity and allure. Despite often being overshadowed by the popularity of Mars or the gas giants like Jupiter and Saturn, Venus is a planet that, especially in this historical phase, deserves our full attention. It's a natural laboratory for studying runaway greenhouse effects, a warning to understand the delicate balances that govern planets, and perhaps one day it might even reveal clues about the possibility of life in extreme conditions. Alright folks, you decide whether Venus deserves to be called Earth's twin sister or not. I don't hear any dissenting voices, and indeed with an average diameter of 12,103 kilometers, about 7,520 miles, roughly 95% that of Earth, and a mass that's 81.5% of Earth's, who could deny that in terms of size and physical characteristics, Venus and Earth look like two planets separated at birth? These similarities also extend to their density, 5.2 grams per cubic centimeter for Venus compared to Earth's 5.5 grams per cubic centimeter, and surface gravity. On Venus, you'd weigh about 90% of what you do on Earth. You'd feel just a bit lighter. But it's not just about size. The two planets also formed in the same region of the solar system, which means they have very similar chemical compositions, with one little difference. While Earth turned into a green and blue paradise, Venus turned into a toxic inferno, an incredibly hot, dry world that's absolutely hostile to any form of life, to the point where one of the current goals of planetary scientists is to understand how our twin transformed this way. It's not just scientific curiosity. Understanding this could teach us something about the climate changes happening here on Earth too. But let's take it step by step. Venus is, after the Moon and the Sun, the brightest object in the sky, and its brilliant presence in the warm hues of twilight has always sparked curiosity and admiration. The planet is called Hesperus when it's the evening star and appears after sunset, and Lucifer when it's the morning star and precedes the sun at dawn. This happens because, like Mercury, Venus is one of the inner planets of the solar system, meaning its orbit around the sun is closer than Earth's. And due to orbital geometry, this means we'll never see Venus more than 47 degrees away from the sun, maximum elongation. For Mercury, the same thing happens. Its maximum elongation doesn't exceed 28 degrees. Its brightness surpasses Sirius by 20 times and Jupiter by 6 times. And at its brightest, it can't even cast a noticeable shadow on Earth. Even in broad daylight with a clear sky, it's possible to spot it with the naked eye. Its particular brightness is due not so much to its size, similar to Earth's, but rather its frequent proximity to our planet and the reflective nature of its cloud cover. And because of those impenetrable clouds, until half a century ago, Astronomers had to make do with calculating that Venus orbits the Sun in 224.7 days, at an average distance of 108 million kilometers or 67 million miles, about 0.72 times the Earth-Sun distance. And that its orbit is the least eccentric of any planet, deviating from a perfect circle by only about 1 part in 150. For Earth, just to understand, this value is 1 to 60, while for the most eccentric orbit, Mercury's, the value is 1 to 5. And while Venus and Earth dance around the Sun, the distance between them varies from a minimum of 42 million kilometers or 26 million miles to a maximum of 257 million kilometers or 160 million miles. Similar to the Moon, the portion of Venus's surface visible from Earth is not always fully illuminated, and the variation in illumination during its orbit creates phases. As these phases change, so do the apparent diameter and brightness perceived by an observer on Earth. The full phase, during which the side of the planet facing Earth is fully illuminated, occurs when Venus is in superior conjunction with the Sun and is not visible from our planet. At inferior conjunction, Venus's apparent diameter reaches its maximum value of 66 arcseconds, and it's in its new phase, with the side facing Earth almost completely in shadow. But of course, Venus's phases aren't an intrinsic aspect of the planet, but a consequence of its orbit and its position relative to us and the Sun. So what's its real nature? Because of the thick, continuous clouds, nothing was known about it before the 20th century. For example, did the planet rotate? And at what speed? Well, it's hard to believe now, but Venus's rotation period was measured using the Goldstone radio telescope in California only in 1961, and its retrograde motion was definitively confirmed only in 1964. Yes, you heard that right. Until the 1960s, when the era of radar measurements began, we didn't even know the rotation period of our closest planet, nor the tilt of its axis. And the radar measurements delivered astonishing data, revealing that Venus's rotation is truly unusual. The planet rotates around its axis very slowly, completing one rotation approximately every 243 Earth days. It's the only planet in the solar system that takes longer to rotate around its axis than to orbit the Sun. These two motions combine in such a way that one day on Venus, the time it takes for the Sun to appear directly overhead, set, and then rise again directly overhead lasts about 117 Earth days. Because of its slow rotation, Venus has retained an almost spherical shape compared to Earth and most other planets. The rotational force of a planet generally causes a bulge at the equator and flattening at the poles. These distortions are minimized on Venus. Then there's the fact that Venus rotates in a retrograde motion, meaning in the opposite direction to most other planets in the solar system. 6 of the 8 planets rotate counterclockwise as viewed from above the North Pole, while only Venus and Uranus rotate clockwise. For an observer on Venus, the Sun would appear to rise in the west and set in the east, if you could see through the thick clouds. Venus's axis of rotation is tilted by only about 3 degrees relative to its orbital plane. This means the seasonal variations on the planet are likely very mild. Unlike Earth and most other planets, Venus does not have a global magnetic field, and this might also stem from its extremely slow rotation. Scientists think that a planet's rotation helps drive fluid movements in its core that generate a magnetic field. And there's more. Although there's no unanimous agreement on this, Venus's rotation seems to be somehow synchronized with Earth's position along its orbit. So much so that when the two planets get close, Venus always shows us the same face. A phenomenon surely due to a still unresolved combination of gravitational interactions. But let's move on, or rather, let's stay a bit longer in the 1950s, when astronomers could only speculate about what Venus might be hiding under its blanket of clouds, and dream of a warm, humid world like our rainforests, the only planet besides Earth likely capable of hosting even evolved forms of life. A romantic dream destined to clash very soon with a harsh reality. Under the absolute white of its clouds, Venus hid a dark secret, a horrendous face, and an infernal environment where it's difficult, if not impossible, to imagine any form of life. As it would soon become known, Venus's surface is covered with black, scaly, sterile volcanic rocks, crisscrossed by solidified lava rivers expelled from hundreds of volcanoes. The atmosphere is very dense. The surface atmospheric pressure is 90 times that of Earth, similar to being 1,000 meters or about 3,280 feet underwater. That's roughly the maximum depth at which our submarines operate, though research bathyscapes and rescue vehicles can go much deeper. The atmosphere is mostly composed of carbon dioxide with nitrogen and traces of sulfuric acid, hydrogen chloride, and hydrogen fluoride. These substances precipitate on the surface as acid rain, quickly destroying machinery like spacecraft landing on the surface. The clouds aren't made of water droplets like on Earth, but sulfuric acid droplets. The sun's rays weakly filter through the dense, sulfurous atmosphere, casting an ugly, yellowish tint on the surface. Before the space age, few of these details were known. Only the general composition of the atmosphere, its high density, and its temperature, which is undoubtedly the least favorable aspect for life on the planet. In 1956, Cornell H. Mayer, a pioneer in radio astronomy, and his colleagues at the United States Naval Research Laboratory observed Venus in the microwave frequency. They discovered that its surface had a much higher temperature than Earth's, so hot it could melt lead. The first spacecraft to visit Venus was Mariner 2, an American probe that performed a flyby in 1962. The initial plan was to launch the probe with a new rocket, which had some development issues. So they had to settle for an earlier, smaller rocket with a lower payload capacity. Consequently, the instrumentation on Mariner 2 was significantly reduced from the original plan. Nevertheless, the mission was successful. The radio astronomical studies from 6 years earlier had probed Venus's atmosphere from afar, but couldn't provide a definitive answer. The most important scientific result of Mariner 2 was confirming up close that Venus's surface temperature is very high, over 400 degrees Celsius or 752 degrees Fahrenheit. In the 1960s and 1970s, other Mariner probes were launched, but we owe our detailed knowledge of Venus's surface mainly to a series of Soviet landers that parachuted below the clouds. In the 1960s, NASA focused on the Apollo program, which would put the first man on the moon, in line with the challenge issued by President Kennedy in a famous 1962 speech. We chose to go to the moon. Meanwhile, the Soviet Union dedicated most of its space missions to the closest planets, Venus and Mars. The scientific exploration of Venus began in 1967 with the Venera spacecraft series, initially designed by aerospace engineering pioneer Sergei Korolev. Like Mariner 2, the first Venera probes limited themselves to flybys of the planet to gather data using remote sensing techniques. Later, other vehicles were parachuted into Venus's atmosphere to directly measure its properties during descent, which lasted about an hour. The probes were battered by strong winds, reaching up to 320 kilometers per hour, or about 200 miles per hour. This is because compared to the solid planet, Venus's atmosphere rotates very quickly. As we mentioned before, the planet completes a full rotation on its axis in 243 days. But the higher regions of the atmosphere at the equator take only 4 days to circumnavigate the planet, with wind speeds varying from around 360 kilometers per hour or about 220 miles per hour in the upper atmosphere to just a light breeze at the surface. To withstand the intense heat and corrosive acids in the atmosphere, the Venera landers had to be heavily armored. They looked more like sturdy steam locomotives than spacecraft. The engineers who built them knew they would be parachuted into an environment with prohibitive conditions, including nightmarish atmospheric pressure. The first to successfully land on Venus was Venera 7 in 1970. Something went wrong during the descent, which was much faster than expected. The spacecraft hit the ground at the speed of a car in a severe accident, damaging the instruments. Fortunately, the lander was robust and didn't get destroyed. It only toppled over, but the side with the radio antennas ended up pointing away from Earth. Despite this, for 20 minutes, a faint radio signal managed to send information about the planet's surface. Venera 8, however, was the first probe in the entire series, 1972 to 1984, to land successfully. Typically, after landing, each vehicle would last at most an hour before the heat and atmospheric conditions caused the instruments to stop functioning. The missions showed that Venus's thick clouds didn't reach the planet's surface, but visibility of the landscape was still limited. The landers spotted hills no more than 3 to 5 kilometers or about 2 to 3 miles away, while at their feet they saw black slabs of magmatic rock, scattered and cracked. The nature of the farther landscape remained mysterious. Studying Venus in the classic way by trying to light the environment with spotlights had strong limitations. Radars, however, could penetrate the clouds, forming the basis of subsequent exploration. After some experimental investigations, significant progress was made with 2 Venera missions, Venera 15 and Venera 16, both launched in 1983. These probes were equipped with wide coverage radar systems, with a spatial resolution of about 1 kilometer or 0.6 miles, and a height resolution of about 50 meters or 165 feet. The missions identified recognizable volcanic features and other decidedly unusual. Venus had shield volcanoes and numerous volcanic cones, structures we know well because they are also present on Earth. But there are others that don't exist on our planet, such as coronae, large circular structures that had previously been mistaken for meteorite craters filled with lava. Not exactly volcanoes as we understand them on Earth, but rather typical annular structures created by liquid lava escaping from an underlying caldera and forcing its way through cracks in the lithosphere. A similar process on Earth formed the volcanic islands of Hawaii. In areas where these coronae form, the crust undergoes concentric collapses that produce rings with diameters ranging from 100 to 1,000 kilometers, or about 62 to 621 miles. Over 500 coronae have been identified on Venus, many of them located on the highest plains, the regions most affected by crustal compression. The authors of the study propose examining the morphology of these coronae using ultra-high-resolution simulations and using them as indicators of recent outbursts of magmatic material from the mantle. Then there are the arachnoids, collapsed domes with radial cracks that resemble spider legs. Both these structures signal the underground presence of stationary hotspots, which generate bubbles of magma within the planet's crust. Venus doesn't have moving tectonic plates colliding with one another, so its volcanoes aren't aligned like those on Earth along the Pacific Ring of Fire. They're scattered pretty much everywhere. The breakthrough in studying Venus's surface came with an important mission, the first interplanetary mission by NASA after an 11-year hiatus. Launched from the Space Shuttle in 1989, the Magellan probe reached Venus in 1990 and orbited the planet for 4 years. Its name was a clear homage to Ferdinand Magellan, the explorer who first circumnavigated Earth. The probe's central body, the module, was ingeniously assembled in a low-cost operation using spare parts from previous missions, and it was equipped with radar to map Venus. To outdo the Venera missions, NASA boosted the radar resolution from 600 to 100 meters, about 200 to 328 feet, allowing Magellan to see geographical details roughly the size of a soccer field. The probe didn't orbit along Venus's equator. It traveled from north to south and then back up, flying over the poles and completing an orbit every 3 hours, while its orbital plane remained fixed in space as the planet rotated beneath. In doing so, the probe observed almost the entire planet, mapping one slice after another and creating a radar image that revealed the ups and downs of the terrain, that is, its geomorphology. Venus's glory was unveiled, and its secrets were finally in plain sight. Magellan revealed that almost 3/4 of Venus's surface is a volcanic landscape. There are almost 100 shield volcanoes similar to Hawaii's Mauna Loa, and hundreds of thousands of smaller, isolated volcanic cones like Mount Etna. In general, Venus's volcanoes cover larger areas, although they aren't taller than those on Earth. The tallest volcano, the Maxwell Montes Massive, reaches 11,000 meters, or 36,089 feet, comparable to the height of Mauna Loa measured from the ocean floor. The channels of solidified lava which flow down the slopes of these volcanoes appear as sinuous lines of irregular, distorted rocks, similar to lava flows on Earth but much longer and broader. These differences are probably due to variations in the composition of the surface rocks. Those on Venus must be more ductile. About 10% of Venus's surface is covered in dust that has accumulated on the plains, blanketing everything. This dust comes from the erosion of the highlands, which in turn is driven by chemical reactions between the rocks and the atmosphere. Since there isn't much water on Venus, only a little in the atmosphere, the erosion isn't caused by water as it is on Earth. Instead, it's partly due to wind, which lifts the dust and wears away the remaining rocks, and partly due to meteorite impacts that shatter the surface rocks and spread fragments everywhere. Venus is as rich in volcanic craters as it is poor in meteorite craters. Only about 1,000 meteorite craters have been identified, many fewer than those on Mercury and the Moon, both of which lack an atmosphere, yet many more than those known on Earth. Terrestrial craters have largely vanished because they are eroded by atmospheric phenomena and because the movement of tectonic plates continually renews the surface. On Venus, there are atmospheric processes, but no tectonic recycling. The reduced number of craters is partly due to the atmosphere protecting the surface from impacts, as meteors tend to disintegrate before reaching the ground. In fact, many craters appear in clusters, as if formed by fragments of a meteor that broke apart without being completely destroyed and fell together. However, the main reason for the scarcity of craters is that in terms of planetary age, the surface of Venus is as young as Earth's, despite lacking active tectonic plates. Perhaps in the past there were more craters, but they have since been covered by new volcanic material and now lie beneath the surface. By linking the number of craters to the frequency with which asteroids hit the planet today, astronomers have estimated that Venus's surface is about 500 million years old. This means 3 or 4 billion years or more of the planet's history remain hidden, a secret beneath its relatively fresh surface, a past wiped clean like a secret agent's changed identity. Has the renewal of the surface occurred gradually over the past 500 million years? Or did it happen all at once about 500 million years ago? It's likely that today there are some active volcanoes on Venus, and in a couple of cases, volcanic ash emissions have been observed. The recent European space mission, Venus Express, identified hotspots on the flanks of some volcanoes, suggesting that beneath their surfaces there are pools of glowing lava, even though no true eruption has ever been observed. Venus is geologically active, but not very much. This suggests that the period of intense volcanic activity dates back a long time. The volcanic activity that renewed Venus's surface was a catastrophic event. What was the cause? Was the entire planet consumed by the fire of volcanoes unleashing all the pent-up rage inside? Or was the lava flow triggered by an external factor? For now, this phase in Venus's history remains a mystery. The renewal spurred by volcanic activity wasn't the only global catastrophe to hit the planet. Today, no trace of water remains on its surface. But according to astronomers, when Venus formed 4.6 billion years ago, and for a period thereafter, it likely wasn't very different from Earth. In fact, it's reasonable to think that at birth, all the terrestrial planets, Mercury, Venus, Earth, Mars, shared similar conditions. Essentially, all newborns look alike. As they matured, however, these planets became distinct individuals, both because small natural differences grew over time and because they were educated in different environments. If it's plausible to support that liquid water once graced Venus's surface, delivered by asteroids and comets, then the planet likely also had an atmosphere made up of nitrogen, water vapor, carbon dioxide, and methane produced by volcanic eruptions. The carbon dioxide and methane would have created a powerful greenhouse effect, further amplified by water vapor as the oceans evaporated due to Venus's proximity to the Sun. The greenhouse effect is a property of certain gases in a planet's atmosphere. On Earth, it's crucial because it keeps the surface at a relatively constant temperature conducive to sustaining life. It was Joseph Fourier, the French mathematician and physicist, who discovered the greenhouse effect of Earth's atmosphere in 1827. Earth receives sunlight and absorbs about 70% of it. The absorbed energy warms the ground, the atmosphere, and the oceans. The warm masses then radiate heat back into space as infrared radiation, which is largely absorbed by greenhouse gases and clouds in the atmosphere. Rather than dispersing into space, the infrared radiation rises the temperature in both layers of the atmosphere. In this way, the heat from the ground and oceans can't escape, and the surface and lower atmosphere keep getting warmer, much like a greenhouse, and that's where the analogy comes from. From the very beginning, the greenhouse effect on Venus was much more intense than on Earth. The planet heated up to the point where its oceans completely evaporated. This happened long before the volcanic resurfacing wiped out any traces of those oceans, rivers, or water-formed minerals. All the water vapor that ended up in the atmosphere only worsened the original greenhouse effect, pushing the temperatures even higher. The atmospheric composition changed, and other greenhouse gases formed, like clouds made of tiny sulfuric acid droplets. As a result, the temperature kept climbing and so on. This explanation was proposed in 1961 by Carl Sagan, an astronomer at Cornell University, to account for Venus's extremely high temperatures. Its runaway greenhouse effect had spiraled completely out of control. Today, the greenhouse effect completely dominates Venus's climate, driving its temperatures up to 500 degrees Celsius or 932 degrees Fahrenheit. On Earth, by comparison, it only brings the temperature up to about 33 degrees Celsius or 91 degrees Fahrenheit, which, while considerable for our climate, is beneficial and not catastrophic. However, the human-produced or anthropogenic greenhouse gases generated by industrial activities in livestock farming, carbon dioxide from burning fossil fuels, and methane from cattle are causing Earth's temperature to rise, threatening to disrupt this delicate balance. The Paris Agreement of 2015 outlined the necessary steps to keep our planet's overall temperature from increasing more than 1.5 to 2 degrees Celsius, or 2.7 to 3 degrees Fahrenheit, above pre-industrial levels by limiting these emissions. Of course, no such controls have ever been applied on Venus, and its natural greenhouse gas emissions have increased far more dramatically than what we're experiencing here. Today, the planet is a hellish landscape of extreme temperatures and bare, arid, and sterile rocks. A horror movie scenario that vividly demonstrates the catastrophic effects of climate change. For Earth, a 2-degree increase in global temperatures might seem like a minor issue, especially compared to the 500-degree surge that Venus once experienced. But even such a small increase could prove disastrous, not necessarily for the survival of our planet, but at the very least for the future of our species. In the end, Venus stands as both a fascinating enigma and a dire warning. As we peel back its thick, acidic clouds and uncover the secrets of its runaway greenhouse effect, we're reminded of just how delicate the balance is between a habitable world and a hostile inferno. Venus may have lost its oceans long ago, and with them any chance for life as we know it. Yet its story is crucial for us here on Earth. It shows us that even small changes in our own atmosphere, whether from nature or human activity, can have catastrophic long-term consequences. Whether it's 15, 20, or 30 years from now, there's no doubt that our destiny will eventually lead us to Mars. We'll get familiar with the moon first, and then we'll take the big leap. In this exploration, the most challenging one humanity will face, there will be no room for even the slightest mistake. There will be no one to help our astronauts. They'll have to do everything on their own, relying solely on their skills and the resources on board to handle the inevitable emergencies. The members of the first crew to attempt this feat are probably already among us, perhaps very young and still unaware. Mars is the red planet, red like blood, a fitting color for the god of war it's named after. In the sky, the planet is easily recognizable. Nothing shines with that color and brightness except for the star Antares, whose name fittingly means rival of Mars. Of all the planets in the solar system, Mars is the most similar to Earth. It's significantly smaller with a diameter half that of Earth. It's also much colder and drier, but 4.6 billion years ago, it was like Earth, warm and wet, with a thick atmosphere and abundant water. If humans had been around on Earth back then, they would have looked up and seen a blue planet, not a red one. Everything changed around 4 billion years ago when things took a turn for the worse. Like Venus, Mars experienced a global climate catastrophe. The reason, unknown until recently, lies in its core. It's hard to determine this just by observing the planet through a telescope, although today even telescopes used by amateur astronomers can easily show the features of the disk of Mars. Galileo was the first to observe the planet with a telescope in 1610, but the instrument was too small and the view too blurry to distinguish surface features. The first surface feature of Mars was discovered in 1659 by Dutch astronomer Christian Huygens. He saw a dark triangular mark, drew it, and described it as a large pond. At the time, it was thought that the gray spots on the moon were oceans, seas, and Huygens followed that line of thinking. In reality, both topographical features are caused by the different coloration of certain minerals and rocks compared to the rest of the surface. By tracking the repeated appearances of this triangular mark, Huygens was able to determine the rotation period of Mars, its day. A Martian day is called a sol and lasts just 37 minutes longer than Earth's 24-hour day. Mars is twice as far from the Sun as Earth, and its year is much longer, 687 Earth days compared to our 365. The tilt of its axis is similar to Earth's, 25.2 degrees, compared to our 23.5. Consequently, day and night alternate just like on Earth, and so do the seasons, but winters are much colder and last longer. The orbit of Mars changes over time, and with it, the cycle of seasons and climate. Currently, surface temperatures range from 20 degrees Celsius during the day to minus 140 degrees Celsius at night. On Earth, the coldest place is Dome Fuji, a research station on the Antarctic Plateau where temperatures drop to minus 80 or minus 90 degrees Celsius at most. In 1666, Italian-French astronomer Gian Domenico Cassini discovered that Mars has polar ice caps. Through a telescope, these appear as white spots at the planet's poles. One grows while the other shrinks, and vice versa, depending on the changing seasons. The polar caps are deposits of ice and dry ice 2 to 3 kilometers thick, with steep cliffs at the edges. The surrounding plains are also covered with dry ice, solid carbon dioxide, which sublimates with the changing seasons. Sublimation is the process where a substance transitions from a solid to a gas without passing through the liquid state. As for water ice, it usually melts and turns into liquid before becoming gas, vapor, but it sublimates if the atmospheric pressure is low, like on Mars. In spring, as the ice grip loosens, the ground on the slopes is freed and slides downhill, raising clouds of red dust. On Mars, the northern polar ice caps shrink in the warmer summer when its northern hemisphere leans towards the sun. They grow again during the colder winter when the North Pole is oriented away from the sun. The same thing happens in the south. Mars and Earth are the only planets in the solar system with polar ice caps that wax and wane with the approach of winter and summer. So, the seasons on Mars vary like those on Earth. The seasons differ in length more than they do on Earth because the orbit of Mars has greater eccentricity than Earth's. For instance, northern hemisphere spring lasts for 194 sols, while fall lasts for only 142 sols. But when did we start to understand that Mars could be a planet similar to Earth? In 1840, Wilhelm Beer, a German banker and amateur astronomer, created the first maps of Mars with his colleague Johann von Madler. They reproduced the dark areas that remained in fixed positions, initially described as water basins. However, the spots had variable color and intensity, and in 1860, French astronomer Emmanuel Liais suggested they were vegetation, thinking the changes were due to the seasonal cycle. It was eventually discovered that they were changes in visibility caused by dust storms. In 1877, Italian astronomer Giovanni Schiaparelli mapped the surface of Mars, classifying the dark shapes as continents, islands, and bays. He also seemed to see numerous long, straight channels connecting some landscape features. Percival Lowell, an American businessman, invested his wealth in building an observatory in Flagstaff, Arizona, to search for Pluto and study Mars. He also saw the color changes in the dark areas and linked them to the changes in the polar caps. When a cap shrank, a dark, irregular greenish-blue band formed around the edge, which then disappeared as the cap shrank further. Then, a dark wave flowed into the channels towards the equator. It was as if a large amount of water was revitalizing the vegetation, just like the seasonal floods of the Nile Valley. Lowell was not familiar with Schiaparelli's map and hoped there was life on Mars. He interpreted Schiaparelli's channels as canals, meaning artificial constructions rather than natural formations. This led him to conclude that the canals were dug by Martians to create an irrigation system and alleviate the perennial drought by channeling water from the polar caps. The belief spread that Mars was a dying, arid world, but not only that. Fueled by novels like The War of the Worlds, it became a common belief that its inhabitants intended to invade and colonize Earth. Less fancifully, in 1877, American astronomer Asaph Hall discovered two satellites orbiting Mars. The larger inner moon is Phobos, fear, and the smaller outer moon is Deimos, terror. The satellites are named after the sons of Ares, who accompanied him in battle. Like Earth's moon, they revolve around their planet in the same time it takes them to rotate, so the same side always faces Mars. In that sense, they are moons, but otherwise they are very different from our moon. Phobos skims above Mars 3 times a day at a height of about 6,000 kilometers or 3,700 miles, while Deimos takes slightly more than a day to orbit Mars at about 23,000 kilometers or 15,000 miles above it, roughly 6% of the Earth-Moon distance. No other satellites in the solar system travel so close to their primary. Undoubtedly, a mission to either would find chunks of Mars in the form of meteorites. While both are cratered, Phobos boasts a crater nearly half its width. They contain too little material for their internal gravitational attraction to shape them into round worlds. Phobos also has grooves that may be the result of tidal stretching. The mean radius of Phobos is 11 kilometers or 6.8 miles, whereas Deimos is only 6.2 kilometers or 3.9 miles. In fact, they look more like captured asteroids than the Moon. Although today Phobos and Deimos can be seen occasionally eclipsing the Sun from the Martian surface, their sizes and distances prevent them from completely covering the solar disk. They are among the tiniest satellites in the solar system. Small as they are, their situation cannot last. Phobos is literally inching towards the Martian surface and cracking up. In less than 50 million years, Mars may lose a moon but gain a ring system. This discovery further reinforced the idea that Mars was a planet quite similar to Earth. But all this ended with the new century. In 1909, at Meudon, just outside Paris, observing the planet with a large telescope, Greek-born French astronomer Eugenios Antoniadis concluded that the channel should be considered merely an optical illusion due to the humanized tendency to interpret point light, and dark spots observed with modest magnification through the Earth's atmospheric shimmer as geometric structures. There was, therefore, no truth in imagining a Martian civilization entirely devoted to building irrigation canals for the planet. Doubts that Mars could host changing vegetation continued almost to the present day, and only with the advent of the space age did the illusion of an inhabited world finally fall. The first mission to visit Mars was Mariner 4, which, after nearly 8 months of flight, flew over the planet on July 15, 1965, at an altitude of only 9,846 kilometers, continuing along the circumsolar trajectory it was on. During the closest approach, it transmitted 11 images of the Martian surface for about 25 minutes, and the 7th frame showed something unexpected. The planet's surface appeared completely arid and heavily cratered. These photographs dispelled any illusions of the presence of life forms, even if only plant life. The red planet thus became for everyone the dead planet. The first spacecraft to orbit Mars, and indeed the first to orbit a planet other than Earth, was Mariner 9, which arrived on November 14, 1971. At that time, a dust storm was raging across the entire planet, hiding its surface. The scientists saw nothing but a yellowish haze, and there were long faces in the control center at such bad luck. Dust storms are a frequent phenomenon on Mars. Often, they are small tornadoes, like those on our planet known as dust devils. On Mars, dust devils roam the desert, moving at high speeds and changing direction in a way that seems both intentional and wild. They stir up the ground, revealing the dark material beneath the red surface dust. From space, this dark material looks like a scribble in the desert, traced by the dust devil on its path. Martian dust storms can be much larger than individual tornadoes. Sometimes they are so massive that they are visible from Earth. They obscure topographical features and can last for months. They lift the lighter dust, and from the surface of Mars, they completely block out the sun. The winds carry the sand everywhere, covering the entire planet, including the polar ice caps, which take on a layered structure like a chocolate and cream cake. A layer of dust covers the ice, then the ice reforms and gets covered again. Dust storms occur mainly in summer when convective motions create strong winds that lift the dust. The most intense storms hit the planet's southern hemisphere. This is because when it's summer in the southern hemisphere, Mars is significantly closer to the sun than when it's summer in the northern hemisphere. Consequently, the southern summer is hotter, so the convective motions are stronger and create more powerful dust storms. Once started, the largest storms can last for weeks or months. Just like with Mariner 9, which had to wait patiently in orbit for the dust to settle, which happened too much later in mid-January of 1972. The long wait was rewarded, however. The probe revealed that the surface of Mars, contrary to what Mariner 4 had shown, which had evidently managed to photograph only a limited portion of the surface, had a certain variety. First of all, Mariner 9 identified recently formed volcanoes. The most impressive of these is Olympus Mons, standing 25 kilometers tall. Think of Everest, which at 8,848 meters is the highest mountain on Earth. Olympus Mons is nearly 3 times taller. The largest volcano on Earth by volume is Mauna Loa, which makes up most of the big island of Hawaii and rests on the Pacific Ocean floor. Well, Olympus Mons has a volume 100 times greater, and its size justifies its grand name, as in Greek mythology, Mount Olympus was the home of the gods. In the same region of Mars, the Tharsis region, there are several other volcanoes. All around, there are lava flows that look recent, perhaps only a few million years old, but no eruptions or active lava flows have ever been observed, and there doesn't seem to be any violent seismic activity either. Additionally, Mariner 9 discovered a massive tectonic rift, which was named Valles Marineris, Mariner Valley, in honor of the probe. The system stretches for 4,000 kilometers or 2,485 miles east-west along the equator, is 600 kilometers or 373 miles wide, and 7 kilometers or 4.35 miles deep. It's a complex of geological fractures 10 times longer, 7 times wider, and 7 times deeper than the Grand Canyon. It's the largest known structure of its kind in the entire solar system, extending for about a quarter of the circumference of Mars. However, Mariner 9 also showed that the most common terrain type on Mars is vast, arid plains of red or yellow, similar to the rocky deserts on Earth. A turning point in discovering many of the secrets of Mars came with the 2 Viking missions of 1975-1976. Each mission involved a spacecraft composed of 2 parts, a lander and a mother capsule that remained in orbit around the planet after releasing the lander onto the surface. The 2 landers were the first to touch down on Mars. Viking 1 remained operational for 6 years and Viking 2 for 3. They searched for biochemical traces but found none. The surface appeared sterile. It seems there is no life on the surface of Mars, or if there is, it doesn't have the properties tested by the landers during experiments conducted directly on the Martian surface. The big surprise came with the discovery that vast areas of Mars must have once been covered by water. The two missions demonstrated this by identifying geological structures that usually form in the presence of water. There were perfectly flat areas with enclosed basins. Evidently, this was material accumulated at the bottom of ancient lakes. The lakes had formed layers of clay. In common language, the word clay has a broad meaning, but in geology it has a technical significance that goes beyond the material's appearance. Later, those layers were studied with satellites orbiting the planet to determine their chemical composition, and it emerged that they were made up of minerals deposited by water, definitive proof that certain areas of Mars were once under still bodies of water. Other clues to the presence of water are the drop-shaped islands, elevated rock formations compared to the plains, extending downstream of obstacles like crater walls. The shores of those islands, now surrounded by arid land, look like cliffs hundreds of meters high, which must have been swept and eroded by devastating floods. Some plains also turned out to be scattered with rounded boulders, probably pushed and shaped by currents. Essentially, there was increasing evidence of abundant water on Mars in ancient times. Scientists have named this period the Noachian, inspired by Noah and the Great Flood. But where and why did all that water disappear? And more importantly, could this mean that Mars might have once hosted life? Questions that, at the time, had no answers. Starting in the 1980s, Mars exploration accelerated. Fewer launchers, but longer missions that made many more discoveries. Since 2010, there have always been 4 to 8 active vehicles on the planet and in its orbit. The ones that usually generate the most excitement among space mission enthusiasts are the rovers, which land on Mars and traverse its surface. The first ones were the size of a coffee table, while the current ones are the size of a car. The total distance they can travel has also increased from 100 meters to tens of kilometers. Communicating with Earth, the latest rovers can choose an interesting point to visit and reach it in a partially autonomous manner. This is a significant advancement because a radio signal can take up to 25 minutes to travel from Earth to Mars or vice versa, so it could take an hour from when the rover sees an obstacle to when it receives the command from Earth to go around it. The studies conducted by rovers over these decades include mapping the surface, analyzing rock composition, and investigating the atmosphere and magnetic field. Mars has a very thin atmosphere, with surface atmospheric pressure of about 0.6% of Earth's. However, it is sufficient to partially protect the surface from solar and cosmic radiation, and can be used for aerobraking maneuvers by spacecraft. The thin atmosphere is responsible for the surreal appearance of the Martian landscape due to the strange color of the sky. It is incapable of retaining blue and violet solar radiation, which makes Earth's sky blue. Additionally, frequent and violent dust storms leave a large amount of dust suspended, coloring the sky pink. Besides being thin, the atmosphere is also very shallow, only a few kilometers thick. Among the most curious discoveries, which long made people think of finding traces of life, is something related to the red color of the planet due to the layer of dust covering its surface, permeating the atmosphere and tinting the sky orange. The dust consists of various types of hematite, a red or orange iron oxide similar to rust. This mineral typically forms in water and has been found in abundance in the region of Mars called Meridiani Planum. In 2004, the rover Opportunity landed in that area to investigate, based on the assumption that if there was once abundant water, then perhaps traces of Martian life remained. Opportunity found areas covered with small spheres made of a type of hematite that forms in water and is less red than usual. When the photos taken by the rover were manipulated to highlight the spheres, the less red hematite turned blue, so the team nicknamed the spheres blueberries. Look at them. It seems impossible that they are just the result of a purely geological process. But speaking of life, there is a significant limitation to its emergence on Mars, represented by the fact that its magnetic field is very weak, almost non-existent. It generally has less than 1% of the strength of Earth's. It is particularly weak above the crust of the northern lowlands of recent formation, and also above large and deep craters and active volcanic areas. It is stronger above the ancient southern highlands, undisturbed by giant meteorite impacts or volcanism. On Earth, the magnetic field is an almost unnoticed presence. Yet the weakness of the magnetic field is why Mars, from a warm and water-rich planet, has transformed into a cold and arid place. Earth's magnetic field mainly derives from an internal dynamo produced by convective motions in the molten iron core. It surrounds Earth and its atmosphere, extending into space even beyond the Moon's orbit, up to 400,000 kilometers high. The volume it encloses is called the magnetosphere, and it is precisely thanks to this structure that the lethal particles emitted by the Sun cannot reach the surface of our planet. Our star is an immense thermonuclear furnace, continuously emitting enormous quantities of charged particles into space, the so-called solar wind. It is also agitated by gigantic explosions during which the solar wind is particularly dense, hot, and fast. After a few days of travel, the solar wind reaches Earth. The impact deforms Earth's magnetic field, confining it to a region called the magnetosphere, which manages to deflect it and keep it away from our planet, making it flow like river water around a bridge pillar. Without this protection, life would disappear in a few weeks. Mars once had a similar magnetosphere generated by a dynamo which magnetized the rocks. We know this because traces of residual magnetism have been found in the planet's oldest rocks. But then the dynamo stopped working. This happened because the convective motions in the molten iron core of Mars ceased. The reason for this interruption is a secret the planet has yet to reveal. Perhaps being very small, the core cooled quickly, becoming first viscous and then solid. Perhaps the internal structure of Mars is different from Earth's, and the mechanism that creates convective motions deep within Earth, whatever it is, does not exist on Mars. Whatever the reason, 4 billion years ago, the disappearance of the magnetic cover opened the doors to the solar wind, which, in addition to sterilizing the planet's surface with its ultraviolet rays and particle radiation, also began to carry away its atmosphere. This task was facilitated by the planet's small size, unable to retain it longer with its mass. There are studies showing that there are precise planetary size limits for supporting life. If planets are too small, gravity is insufficient to retain the more volatile molecules. This could mean that even the presence of an efficient magnetosphere would not have prevented the loss of the atmosphere. So, in the end, with almost all the atmosphere gone, the atmospheric pressure became too low to allow liquid water to exist on the surface. Now, Mars is an arid planet, swept by global dust storms. It is also a frigid world, where winter night temperatures can drop to minus 140 degrees Celsius at the poles. It is the red planet we have come to know, a place that only robotic rovers find hospitable. Could there be a possibility of some liquid water pools on the surface? In fact, for there to be liquid water on the planet's surface, atmospheric pressure would need to be much higher than what it is currently measured. An exception could be the Hellas Planitia crater, which, being the largest and deepest crater on Mars, has a slightly higher atmospheric pressure at the bottom than the triple point. So when the temperature exceeds 0 degrees Celsius, it could contain liquid water. So, my friends, over time, if it had been fortunate enough to retain its magnetosphere, perhaps Mars could have hosted life, even alien creatures like those imagined by H.G. Wells. In that case, we might have truly faced a war of the worlds. But it didn't turn out that way. There remains the hope that in very ancient times, during the Noachian period, primitive forms of life developed that today survive in particularly ecological niches. That would indeed be a secret of Mars waiting to be unveiled. But perhaps there is something else that might give us the fortune to discover that Mars once teemed with life, maybe only at the level of unicellular organisms: meteorites. Because as you know, we now have the certainty that a large number of meteorites found on our planet's soil come from Mars. The history of Martian meteorites has been reconstructed by measuring radioactive elements and their decay products, which remain trapped in the rocks once they have solidified. It has been established that the rocks from Mars were last in a molten state 1.37 billion years ago, a much more recent time compared to most meteorites, which solidified 4 billion years ago or more. It also seems that all Martian meteorites come from a large fragment expelled into space 200 million years ago when an asteroid crashed into Mars. The impact probably also hurled a shower of smaller fragments into space. Perhaps this event caused the grooves radiating from Phobos' nose, or if not this, a similar one. The large fragment moved away from Mars and began orbiting the solar system like an asteroid. A collision with another asteroid 10 million years ago broke it into smaller parts. These fragments scattered in all directions, orbiting in space for another 10 million years, and recently some have fallen to Earth. This story shows that the planets of the solar system, although separated by tens of millions of kilometers, are not entirely isolated from each other. In reality, there are continuous exchanges of material between them. Lunar material falls to Earth in the form of lunar meteorites, and Earth's material is hurled to the Moon. Just as traffic flows both ways between Earth and the Moon, Martian material has fallen to Earth, and Earth's material has surely ended up on Mars. Therefore, a bit of the soil in your garden or the pot on your windowsill, just a bit, comes from Mars. The carrots you eat contain a pinch of the red planet. And just as there is a sprinkling of Martian soil on Earth, so too Earth's soil is found on Mars. Perhaps that soil contained organisms that developed in the favorable terrestrial environment. The most resilient could have survived in space, and the most resilient of all, after hitching an interplanetary ride and falling by chance into hospitable spots on the red planet, could have survived to colonize Mars. And who knows, if one day we find forms of life on Mars, we might discover to our surprise that they came from Earth, and that the Martians are us. History of Jupiter, the Colossus of our solar system. Let's continue our documentary series dedicated to the planets of the solar system, with the goal of comprehensively describing their history and characteristics. After exploring the scorching plains of Venus, the red deserts of Mars, and the torrid little world of Mercury, it's time to leave the inner rocky planets behind and turn our gaze toward the first of the giants, Jupiter, the Colossus of our solar system, so massive that its gravity influences the entire planetary equilibrium. In this new chapter, we won't limit ourselves to describing the best-known features of this imposing planet. Instead, we'll go beyond, exploring its complex atmospheric structure with the iconic Great Red Spot, its extremely powerful magnetic field, its fascinating ring system, and the surprising entourage of moons that accompany it, some of which might harbor subsurface oceans. Comprehensive means exactly this: a detailed account rich with information and insights that will lead you to look at Jupiter with new eyes, appreciating its complexity and hidden charm. Jupiter is a planet of contrasts and decidedly surprising characteristics. The fifth world of our solar system, so massive that it alone contains more than twice the mass of all other planets combined, so large that it could contain over 1,300 Earths within its volume, yet so rapid in its rotation that it completes a turn on its axis in less than 10 hours. So imposing that it creates a magnetic field 14 times stronger than Earth's, but lacking a solid surface to walk on. Its atmosphere, a whirlwind of colored bands and cyclopean storms, hides a world whose composition mirrors the primordial nebula from which the entire solar system was born, a living archive of cosmic origins just waiting to be deciphered. But let's proceed in order and get to know this planet better through its numbers. With an equatorial diameter of 142,984 kilometers, or 88,846 miles, about 11.2 times that of Earth, Jupiter is the largest planet in the solar system. Its mass is approximately 318 times that of Earth, representing 71% of the total planetary mass in the solar system. Despite its imposing dimensions, its density is surprisingly low, 1.33 grams per cubic centimeter, 82.9 pounds per cubic foot, less than a quarter of Earth's, as it is composed primarily of light elements like hydrogen and helium. Jupiter orbits the Sun at an average distance of 778 million kilometers, or 484 million miles, or 5.2 astronomical units, completing a revolution in 11.86 Earth years. Its orbit is relatively a little eccentric, with a value of 0.048, causing its distance from the Sun to vary less than many other planets. The gas giant rotates on its axis in just 9 hours and 56 minutes at the equator. The deep internal rotation is slightly different, about 9 hours and 50 minutes, making it the planet with the fastest rotation in the solar system. This rapid rotation causes a notable polar flattening, with a polar diameter almost 9,300 kilometers, or 5,780 miles, less than the equatorial one. The axial tilt is minimal, only 3.13 degrees, which means Jupiter doesn't experience significant seasons. The temperature in the upper part of the clouds is about minus 145 degrees Celsius, or minus 230 degrees Fahrenheit, while pressure and heat increase dramatically going deeper. The surface gravity, measured at the level of visible clouds, is 2.4 times that of Earth. If you weigh 70 kilograms or 154 pounds on Earth, you would weigh 168 kilograms or 370 pounds on Jupiter. This cold, objective data doesn't tell the true story of this gas giant, however. Its biography is written in the complex patterns of its cloud bands and in its vortices that last for centuries. Lacking a solid surface and with an atmosphere that gradually fades towards a perhaps rocky core, Jupiter represents a type of world completely different from the inner rocky planets. Its clouds, organized in belts and zones of different colors that surround the planet parallel to the equator, are the visible result of powerful jet streams flowing in opposite directions at different latitudes, creating turbulent boundaries where vortices and storms form. The detailed study of Jupiter became possible only after the invention of the telescope, although the planet was known since antiquity as one of the wandering planets visible to the naked eye. Galileo Galilei in 1610 was the first to observe it with a telescope, discovering the 4 major Jovian moons, Io, Europa, Ganymede, and Callisto, now known as the Galilean moons. This discovery was revolutionary, providing one of the first observational proofs that not all celestial bodies orbited around Earth, thus supporting Copernicus's heliocentric model. Since then, Jupiter has continued to fascinate astronomers of every era. The Great Red Spot, perhaps Jupiter's most iconic feature, was first reliably observed by Italian astronomer Giovanni Cassini in 1665. It's an immense anticyclonic storm, large enough to contain 2 or 3 planets the size of Earth, that has been raging for at least 350 years, although in recent decades it has gradually reduced in size. Its reddish coloration is probably due to chemical compounds that are brought to the surface by upward currents and then altered by solar radiation. Jupiter's visible appearance is dominated by the alternation of light and dark bands running parallel to the equator. The light bands, called zones, are regions where gas rises upward in the atmosphere. The dark bands, called belts, are areas where the gas descends. This zonal aspect is the result of the planet's rapid rotation combined with the convective motions of the atmosphere and the Coriolis effect, which bends the ascending and descending currents in opposite directions in different latitude bands. Jupiter's atmospheric composition largely reflects that of the primordial solar nebula, being composed of approximately 89 to 90% molecular hydrogen and 10% helium, with traces of methane, ammonia, hydrogen sulfide, and water vapor. The visible colorations in the clouds are due to the photochemical compounds produced by the interaction between sunlight and these trace elements. In particular, sulfur and phosphorus compounds are responsible for the brownish and reddish tones, while crystallized ammonia forms the higher white clouds. Jupiter's internal structure still presents many mysteries, but current models suggest a layered organization. Below the visible cloud layer, the atmosphere becomes progressively denser until it transforms into an ocean of liquid hydrogen. About 10,000 kilometers below the clouds, the pressure is so high that hydrogen assumes a metallic liquid state, in which electrons are free to move, making hydrogen an electrical conductor like metals. This layer of metallic hydrogen in rapid rotation is believed to be responsible for Jupiter's extremely powerful magnetic field. At the center, probably there is a solid core composed of heavier elements, with an estimated mass between 7 and 25 times that of Earth. This magnetic field is the most powerful among all the planets in the solar system, about 14 times more intense than Earth's, and with a volume 20,000 times greater. Jupiter's magnetosphere is so vast that if it were visible from Earth, it would appear in the night sky as large as the full moon, despite the enormously greater distance. This gigantic magnetic bubble traps charged particles, creating intense radiation belts similar to Earth's Van Allen belts, but much more powerful. The radiation is so intense that it represents a serious danger for space probes approaching the planet, requiring special shielding to protect the onboard electronics. Another notable aspect is Jupiter's ring system, much less showy than Saturn's, but no less interesting. Discovered only in 1979 by the Voyager 1 probe, this system consists of 4 main components: the innermost and diffuse halo ring, the brighter main ring, and the 2 outer rings called gossamer, veil, associated with the moons Amalthea and Thebe. Unlike Saturn's rings, which are primarily composed of ice particles, Jupiter's are formed by tiny dust particles, probably material ejected from the small inner moons due to meteorite impacts. The close-up exploration of Jupiter has been a complex undertaking, given the enormous distance from Earth and the hostile environment surrounding the planet. The first probe to visit the gas giant was Pioneer 10 in 1973, followed by Pioneer 11 in 1974. These missions provided the first close-up images and direct measurements of the Jovian environment, also discovering the existence of radiation belts and rings. The Voyager 1 and 2 probes, launched in 1977, visited Jupiter in 1979 and shortly after, providing detailed images of the clouds and discovering volcanic activity on Io, the first observation of active volcanism outside of Earth. A qualitative leap in Jupiter's exploration came with the Galileo mission, launched in 1989, which reached Jupiter in December of 1995 and became the first spacecraft to orbit the planet. Before entering orbit, Galileo released an atmospheric probe that penetrated directly into the planet's atmosphere, transmitting data for almost an hour before being destroyed by pressure and heat. The mother probe continued to orbit Jupiter for almost 8 years, completing 35 orbits around the planet and conducting in-depth studies of the Galilean moons, including the detection of a probable ocean under Europa's icy surface. The mission deliberately concluded in September of 2003 when the probe was made to plunge into Jupiter's atmosphere to avoid possible contamination of potentially habitable moons in case of malfunction. Other probes that have provided data on Jupiter during close flybys include Cassini-Huygens in 2000, headed towards Saturn, and New Horizons in 2007, headed towards Pluto. Both took advantage of Jupiter's gravitational assist to accelerate towards their final destinations, simultaneously collecting data and images of the gas giant. The most recent and technologically advanced mission is Juno, launched by NASA in 2011 and arriving in orbit around Jupiter in July of 2016. Specifically designed to study the composition, gravitational field, and magnetic field of the planet, Juno orbits on a highly elliptical polar trajectory that brings it to just 4,200 kilometers or 2,610 miles above the polar clouds every 43 days. This particular orbit allows the probe to avoid the zones of maximum radiation and to obtain a complete mapping of the gravitational structure, offering precious clues about the distribution of mass inside the planet. Its instruments, protected by a robust titanium case, include a magnetometer, a microwave spectrometer to study the deep atmospheric composition, an infrared spectrometer to analyze the upper atmosphere, and a visible light camera called JunoCam that has provided spectacular images of Jovian clouds seen from perspectives never observed before. The Juno mission required extraordinary engineering to face Jupiter's hostile environment. To withstand the intense radiation belts, the spacecraft's electronics are enclosed in a titanium vault, weighing 200 kilograms or 440 pounds, which provides shielding equivalent to that of a 9mm thick lead wall. The probe's solar panels are the largest ever used for a planetary mission, with a total surface area of 60 square meters or 645 square feet, necessary to capture the weak sunlight at that distance from the Sun. Despite these precautions, NASA engineers had predicted that Jovian radiation would gradually degrade Juno's instruments, which is why the mission was initially planned to last only 20 months. Surprisingly, the probe has resisted much better than expected, allowing multiple mission extensions. The images sent by Juno show Jupiter's poles as we have never seen them before. A chaotic assembly of octagonal cyclones at the North Pole and pentagonal ones at the South Pole, which remain stable over time, defying our knowledge of fluid dynamics. The probe has also revealed that the atmospheric bands and the Great Red Spot extend much deeper than previously thought, and has provided data suggesting a diffuse rather than compact core. The analysis of the gravitational field has also allowed determining that the winds observed on the surface extend to depths of about 3,000 kilometers or 1,865 miles, involving about 1% of the planet's total mass. Initially scheduled to conclude in 2018, the Juno mission was extended until 2021 and then further until 2025, allowing more complete coverage of the planet and more detailed observations of the Galilean moons. The probe, at the end of its mission, will be deliberately made to plunge into Jupiter's atmosphere, like Galileo before it, to avoid biological contamination of Europa and other potentially habitable moons. Jupiter's moon system is a veritable miniature solar system, with at least 79 confirmed satellites of various sizes. These satellites can be divided into different categories: the 4 large Galilean moons, Io, Europa, Ganymede, and Callisto, an inner group of 4 small moons, Metis, Adrastea, Almothea, and Thebe, that orbit inside Io's orbit, and numerous groups of irregular moons, probably asteroids captured by the planet's gravity at different times, which orbit at great distances with often eccentric and retrograde orbits. Most of these moons, interestingly, take their names from the lovers of Roman deities, thus creating a curious mythological connection. The 4 Galilean moons are the largest and most interesting, each with unique characteristics that make them worlds unto themselves, worthy of dedicated exploration. Ganymede, the largest, is also the largest moon in the entire solar system, with a diameter of 5,268 kilometers or 3,273 miles, even larger than Mercury. It's the only known moon to possess its own magnetic field, probably generated by a molten iron core. Its surface is divided into 2 types of terrain: dark, older, and heavily cratered regions, and lighter regions characterized by numerous parallel grooves, probably formed by tectonic processes. Like Europa, Ganymede is believed to hide a subsurface ocean, located at a greater depth and trapped beneath layers of ice. It might have several overlapping layers of ice and water, as well as a possible global ocean between the ice layers. A unique characteristic of Ganymede is the presence of a tenuous oxygen atmosphere, produced when solar radiation and charged particles from Jupiter's magnetosphere strike the icy surface, splitting water molecules. Its low reflectivity suggests that its surface is probably composed of dark, colorless rock. Io, the innermost of the Galilean moons, is the most volcanically active body in the solar system, with over 400 active volcanoes continuously erupting sulfur and sulfur compounds, creating a multicolored surface dominated by yellows, reds, and blacks. This intense volcanic activity is fueled by heat generated by powerful tidal forces. Io orbits in a 1 to 2 to 4 gravitational resonance with Europa and Ganymede that keeps its orbit slightly eccentric, causing a tidal deformation that heats the moon's interior until it melts. The thermal energy generated is estimated at 10 trillion watts, about 25 times greater than all the energy used by humanity. Eruptions on Io can project material up to 500 kilometers, or 310 miles above the surface, with volcanic plumes visible even from passing space probes. This material, mainly sulfur compounds and sulfur dioxide, falls back to the surface or escapes Io's gravity, feeding the plasma torus that surrounds the Moon's orbit and contributing to Jupiter's magnetosphere. Due to Jupiter's gravitational attraction, Io experiences enormous tides in its solid surface that can reach up to 100 meters, or 328 feet in height. These tides, in turn, generate enough heat for volcanic activity, giving Io its characteristic mottled yellow-orange appearance. Europa, the second Galilean moon, is one of the most promising places to search for extraterrestrial life in the solar system. Its icy surface, one of the smoothest in the solar system, presents a complex network of cracks and ridges, suggesting the presence of a liquid ocean underneath. This ocean, which is believed to contain more water than all of Earth's oceans combined, is kept liquid by tidal heat generated by the gravitational interaction with Jupiter and the other Galilean moons. Europa's surface is relatively young, with few craters, indicating active geological processes that continue to renew it. Detailed images also show chaotic regions where the surface ice seems to have broken and refrozen, perhaps due to convective currents in the underlying ocean or pockets of liquid water near the surface. The presence of a liquid ocean, combined with the energy provided by tidal forces and possible essential chemical elements for life transported by comets or produced by chemical reactions, makes Europa a primary target for future astrobiology missions. NASA is currently developing the Europa Clipper mission, scheduled for launch in 2024, which will repeatedly fly over the Moon to study the composition of its surface and confirm the presence of the underlying ocean. Part of this liquid erupts from Europa's surface in geysers at the Moon's south pole. The prospects of finding life on Europa are particularly intriguing for astrobiologists. Europa's subsurface ocean meets all the fundamental requirements for life as we know it: liquid water, essential chemical elements, and a source of energy. The latter is provided by the tidal forces generated by Jupiter and the other Galilean moons, which keep Europa's interior warm despite its distance from the Sun. Some models suggest that Europa's ocean floor might host hydrothermal vents similar to those on Earth, where complex ecosystems thrive completely independent of sunlight. Moreover, recent observations of water vapor plumes erupting from the surface suggest that it might be possible to sample the underlying ocean without having to drill through the thick icy crust. These characteristics have led many scientists to consider Europa as the most promising candidate for hosting extraterrestrial life in our solar system, surpassing even Mars in terms of biological potential. Callisto, the outermost of the Galilean moons, is the third largest moon in the solar system after Ganymede and Titan, Saturn's satellite. Orbiting at a greater distance from Jupiter than the other Galilean moons, Callisto is not locked in the orbital resonances that cause the intense tidal heating of Io, Europa, and Ganymede. Consequently, it is geologically less active, with an ancient, heavily cratered surface that serves as a record of impacts in the inner solar system. The most notable crater is Valhalla, a concentric ring structure 600 kilometers or 373 miles in diameter. Despite its apparent geological inactivity, Callisto might also have a subsurface ocean, suggested by magnetic field measurements indicating the presence of an electrical conductor under the surface. The duration of a day on Jupiter is determined by how fast it rotates. Being the planet with the fastest rotation in our solar system, Jupiter completes a rotation every 10 hours or so. However, it's important to note that as Jupiter is a gas giant, it doesn't rotate as a solid sphere. Jupiter's equator rotates at a speed of 45,500 kilometers per hour, or 28,273 miles per hour, slightly faster than the polar regions. This causes a slight variation in the length of a day on Jupiter, depending on where you are on the planet. For example, at the equator, a day on Jupiter lasts 9 hours and 50 minutes, while around the polar regions, a day on Jupiter is 9 hours and 56 minutes. A surprising fact concerns Jupiter's role as a cosmic cleaner and planetary shield for the inner solar system. Thanks to its enormous mass and consequent strong gravitational attraction, Jupiter has the power to deflect or capture comets and asteroids that might otherwise head towards the inner planets, including Earth. In 1994, astronomers witnessed a spectacular example of this protective role when comet Shoemaker-Levy 9, already captured by Jupiter's orbit, fragmented into about 20 pieces and impacted the planet between July 16th and 22nd, creating enormous dark scars in the atmosphere visible for months. The impact generated explosions equivalent to millions of megatons of TNT, releasing energies that could have caused a mass extinction on Earth. Computer simulations suggest that without Jupiter's presence, the rate of catastrophic impacts on Earth would be 100 to 1,000 times higher, perhaps making the development of complex life impossible. Some astronomers hypothesize that the presence of a Jupiter in the outer zone of a planetary system might be one of the prerequisites for the development of life on rocky planets in the habitable zone, a true cosmic guardian. We should therefore be grateful to Jupiter for having protected Earth, as it is believed that the planet has played an important role in preventing asteroids from hitting us. As we've seen with the extinction of the dinosaurs, a single asteroid impact of catastrophic proportions could drastically change the course of evolution on Earth. Ultimately, without Jupiter's protective influence, life on Earth might not have developed as we know it today. One of the most fascinating aspects of Jupiter is related to its influence on dwarf planets beyond Neptune and on the overall structure of the solar system. Observations show that many objects in the Kuiper Belt have orbital periods that are integer multiples of Jupiter's, a phenomenon known as orbital resonance. This suggests that Jupiter has played a fundamental role in organizing the entire architecture of the outer solar system, moving planets and debris into specific regions of space during the formation of the system. Some models even suggest that in the first millions of years of the solar system, Jupiter migrated inward to the current orbit of Mars and then back outward in a movement called the Grand Tack, which would have completely reshaped the distribution of material in the protoplanetary disk. This model, known as the Nice model, suggests that initially the giant planets formed much closer to each other than they are today, with Neptune and Uranus in positions more internal than where we currently observe them. The gravitational interactions between these planets and an outer disk of planetesimals caused a gradual outward migration, which at some point became unstable. During this instability phase, which is estimated to have occurred about 700 million years after the formation of the solar system, potentially linking to the period of late heavy bombardment observed in lunar rocks, Jupiter would have moved slightly inward, while Saturn, Uranus, and Neptune would have moved outward, with the latter two possibly even exchanging their positions. The question we all ask at this point is, could there be life on Jupiter? Since Jupiter's atmosphere becomes warmer with depth, reaching a temperature similar to ambient temperature at an altitude where the atmospheric pressure is about 10 times greater than on Earth, scientists hypothesize that if life existed on Jupiter, it would be found at this level and would necessarily be airborne. However, these are just theories, as to date no form of life has been discovered on Jupiter. Although Jupiter itself might not be able to support life as we know it, some of its moons have oceans under their crust that could potentially host forms of life. Europa in particular, with its vast subsurface ocean kept liquid by tidal heat, is considered one of the most promising places in the solar system to search for life beyond Earth. This has led to the design of NASA's Europa Clipper mission, which will explore this moon to determine if it could host conditions suitable for life. If we look even further beyond the boundaries of our system, recent discoveries of exoplanets show us that planets similar to Jupiter are relatively common around other stars. However, many of these extrasolar Jupiters have orbital characteristics very different from ours. The so-called hot Jupiters orbit extremely close to their stars, completing an orbit in just a few Earth days. This contrasts sharply with the relatively distant position of our Jupiter, suggesting that planetary migration might be a common phenomena, but with highly variable outcomes. The particular configuration of our solar system, with the giant gas planets in the outer regions and the small rocky worlds in the inner ones, might be one of the elements that made the development of life on Earth possible. A fascinating curiosity is that if Jupiter had grown even more during the formation of the solar system, it could have become a star. In reality, it would have needed to accumulate about 75 to 80 times more mass than its current mass to trigger hydrogen fusion and become a star like the Sun. However, Jupiter already shows some primitive stellar characteristics. It emits more energy than it receives from the Sun, due to slow gravitational contraction and primordial heat trapped inside. This extra energy, about 67% more than that received from the Sun, is radiated mainly in the infrared. If observed in this wavelength, Jupiter glows faintly with its own light. Some scientists classify Jupiter as a sub-brown dwarf, a body halfway between a planet and a true brown dwarf star. In double or multiple stellar systems, objects similar to Jupiter but slightly more massive are common, orbiting around larger stars just as our gas giant orbits around the Sun. Ultimately, Jupiter continues to amaze and fascinate both professional astronomers and enthusiasts. With its storms that last for centuries, its complex system of moons that are worlds unto themselves, and its crucial role in the evolution of the solar system, the gas giant represents a natural laboratory for understanding the physical processes that dominate objects of this class. As we continue our journey through the solar system, keep in mind that every planet we encounter is not an isolated entity, but part of a complex system of interactions that extends for billions of years into the past and future. Jupiter, with its majestic presence, reminds us that even in the apparently static void of interplanetary space, dynamic and powerful forces are constantly at work, slowly but inexorably sculpting the destiny of our corner of the universe. In the next episode, we'll push even further from the Sun to explore the Lord of the Rings, Saturn, another giant with secrets all its own to reveal. History of Saturn, the solar system's greatest show. We continue our documentary dedicated to the planets of the solar system with the goal of comprehensively describing their history and characteristics. After traversing the scorching plains of Venus, the red deserts of Mars, the torrid world of Mercury, and the colossal storms of Jupiter, it's time to meet the most spectacular of all planets, Saturn, the magnificent Lord of the Rings, so elegant that it has captured humanity's imagination since the first telescopic observation. In this new chapter, we won't simply describe the hypnotic beauty of its ring system, but we'll go beyond, exploring its complex internal structure, its winds that blow at supersonic speeds, the mysterious polar hexagon, and the fascinating family of over 80 moons that accompany it, some of which hide underground oceans and unique geological phenomena. Comprehensive means exactly this: a detailed narrative rich with information and insights that will lead you to look at Saturn with new eyes, appreciating not only its exterior beauty, but also the hidden scientific complexity. Saturn is a planet of surprising elegance, the sixth world from the Sun, so light that it would float on water if there existed an ocean large enough to contain it, so majestic that it's visible to the naked eye from Earth as a golden star, so rapid in its rotation that it completes a turn on itself in just over 10 hours, yet so slow in its orbit that it takes almost 30 Earth years to complete one trip around the Sun. Its rings, extending for hundreds of thousands of miles but only a few yards thick, create an unparalleled cosmic spectacle, while its atmosphere conceals hexagonal storms that defy the laws of physics as we know them. But let's go in order and get to know this planet better through its numbers. With an equatorial diameter of 74,898 miles or 120,536 kilometers, about 9.4 times that of Earth, Saturn is the second largest planet in the solar system. Its mass equals about 95 times that of Earth, but despite its imposing dimensions, its density is surprisingly low, only 0.687 grams per cubic centimeter or 42.9 pounds per square foot, less than the density of water because it's composed mainly of hydrogen and helium. Saturn orbits the Sun at an average distance of 886 million miles or 1.43 billion kilometers, which is 9.5 astronomical units, completing one revolution in 29.46 Earth years. Its orbit is moderately eccentric, with a value of 0.056 that makes its distance from the Sun vary by about 96 million miles or 155 million kilometers between aphelion and perihelion. The gas giant rotates on its axis in 10 hours and 33 minutes at the equator, though like Jupiter, the rotation varies slightly with latitude. This rapid rotation causes polar flattening, even more pronounced than Jupiter's, with the polar diameter being almost 7,460 miles or 12,000 kilometers smaller than the equatorial diameter, giving the planet a distinctly oblate shape. The axial inclination is 26.7 degrees, similar to Earth's, which means Saturn experiences pronounced seasons, each lasting about 7 Earth years. The temperature in the upper cloud layers is about minus 288 degrees Fahrenheit or minus 178 degrees Celsius, while pressure and heat increase dramatically as you descend deeper. The surface gravity, measured at the visible cloud level, is slightly less than Earth's, 0.916 times. So, if you weigh 154 pounds on Earth, you'd weigh about 141 pounds on Saturn. These numbers alone, however, cannot tell the true story of this gas giant. Its biography is written in the complex patterns of its cloud bands, its vortices that last for decades, and in that magnificent ring system that has made it the most recognizable planet in the solar system. Devoid of a rocky surface and with an atmosphere that gradually fades toward a possible rocky core, Saturn represents a completely different type of world from the inner rocky planets. Its clouds, organized in bands and zones of different colors that encircle the planet parallel to the equator, are the visible result of powerful jet streams flowing in opposite directions at different latitudes, creating turbulent boundaries where vortices and storms form. The history of observations. The detailed study of Saturn has been possible only after the invention of the telescope, although the planet was known since antiquity as one of the wandering planets visible to the naked eye. Galileo Galilei in 1610 was the first to observe it with a telescope, but the limited resolution of his instrument made him see the planet as having ears or lateral appendages, without being able to understand the true nature of those protuberances. It was only in 1659 that Dutch astronomer Christian Huygens, using a more powerful telescope he had built himself, managed to solve the mystery. Huygens understood that those ears were actually a thin and flat ring, everywhere detached and not touching the planet, inclined towards the ecliptic. This discovery was revolutionary and forever changed our perception of Saturn. In 1675, Italian astronomer Giovanni Domenico Cassini made another fundamental discovery. What Huygens had described as a single ring was actually divided into two parts separated by a dark space. This gap, known as the Cassini division, was the first indication that the ring system was much more complex than initially imagined. Since then, Saturn has continued to fascinate astronomers of every era, always revealing new details and mysteries. Atmospheric composition and structure. Saturn's atmospheric composition largely reflects that of the primordial solar nebula, being composed of about 96.3 molecular hydrogen and 3.25% helium, with significant traces of methane, 0.45%, ammonia, hydrogen sulfide, ethane, propane, and water vapor. However, the proportion of helium is notably lower compared to Jupiter, which has about 10% helium, suggesting that the heavier helium is slowly precipitating towards the planet's interior through a process called helium rain that significantly contributes to the planet's internal heat. Saturn's atmosphere presents a complex stratified structure. The troposphere, the lowest layer, extends from the visible cloud surface to about 62 miles or 100 kilometers altitude, where temperature varies from minus 288 degrees Fahrenheit or minus 178 degrees Celsius at the surface to about 169 degrees Fahrenheit or minus 113 degrees Celsius at the upper limit. Above is the stratosphere, extending to 621 miles or 1,000 kilometers altitude, where temperature gradually increases to reach minus 45 degrees Fahrenheit or minus 43 degrees Celsius due to absorption of solar ultraviolet radiation by hydrocarbons. Even higher, we find the thermosphere, where temperatures can reach 788 degrees Fahrenheit or 420 degrees Celsius. Winds on Saturn are among the fastest in the solar system, reaching speeds of over 1,118 miles per hour or 1,800 kilometers per hour in the equatorial zone, about 5 times faster than the most powerful terrestrial hurricanes. These supersonic winds are powered by the planet's internal heat and rapid rotation, creating a system of jet streams that encircle the planet at different latitudes. Saturn's atmospheric bands, though less contrasted than Jupiter's, show a complex zonal structure with at least 12 distinct bands of alternating winds. One of Saturn's most extraordinary features is the North Polar Hexagon, a gigantic storm with a perfectly hexagonal shape, with sides of about 8,575 miles or 13,800 kilometers each, large enough to contain 4 planets like Earth. First discovered by the Voyager probes in the 80s and studied in detail by the Cassini mission, this phenomena has no precedent in the solar system. The hexagon rotates with a period of 10 hours and 39 minutes, slightly different from the planet's internal rotation measured through radio emissions. It's accompanied by a vortex at the center of the North Pole that rotates at speeds up to 336 miles per hour or 540 kilometers per hour, with an eye about 1,243 miles or 2,000 kilometers in diameter. The hexagon maintains its precise geometric shape through a mechanism not yet fully understood, but laboratory experiments with rotating fluids have demonstrated that similar polygonal structures can form when jet streams of different speeds interact in rotating systems. The structure extends vertically for at least 186 miles or 300 kilometers into the atmosphere, and its long-term stability, observed for over 30 years, remains one of the most enigmatic atmospheric phenomena in the solar system. At the South Pole, instead, we find a more conventional but equally impressive vortex with a clearly defined eye, about 4,971 miles or 8,000 kilometers in diameter, similar to that of a terrestrial hurricane but much larger. This vortex is surrounded by clouds rotating at speeds up to 342 miles per hour or 550 kilometers per hour and extends vertically for over 47 miles or 75 kilometers into the atmosphere. Unlike the northern hexagon, the southern vortex shows a more chaotic and time-variable structure. Storms on Saturn, though less frequent than Jupiter's, can be spectacular. The Great White Spot is a recurring phenomenon that appears every 29 to 30 Earth years, about one Saturnian year, in the planet's northern hemisphere. These enormous storms can extend for thousands of miles and last for months, temporarily altering the appearance of the entire affected atmospheric band. The last Great White Spot was observed in 2010 by the Cassini mission and extended until it completely encircled the planet. Internal structure. Saturn's internal structure is presumably similar to Jupiter's, but with some significant differences, reflecting its smaller mass and density. At the center lies a core of rocky, icy material with an estimated mass between 15 and 18 times that of Earth, and a radius of about 15,534 miles or 25,000 kilometers, significantly larger than Jupiter's core in proportion to planetary dimensions. This core is composed mainly of rock, water ice, and heavier compounds like silicates and iron, with an estimated density of about 10 to 12 grams per cubic centimeter, or 624 to 748 pounds per square foot, and a temperature that can reach 21,092 degrees Fahrenheit, or 11,700 degrees Celsius, hotter than the Sun's surface. Around the core extends a thick mantle of liquid metallic hydrogen, where pressure is so high, over 3 million times Earth's atmospheric pressure, that electrons are stripped from hydrogen atoms, creating a conductive fluid similar to liquid metal. This layer, about 16,155 miles or 26,000 kilometers thick, is rapidly rotating and generates the planet's magnetic field through the dynamo effect. Temperature in this region varies from about 14,432 degrees Fahrenheit, or about 8,000 degrees Celsius, in the deep part, to 5,432 degrees Fahrenheit, or about 3,000 degrees Celsius, in the upper part. Above the metallic hydrogen lies a vast ocean of liquid molecular hydrogen, about 18,641 miles, or 30,000 kilometers deep, where pressure gradually decreases and temperature drops to about 3,632 degrees Fahrenheit, or 2,000 degrees Celsius, in the deep part, and 320 degrees Fahrenheit, or 160 degrees Celsius, in the upper part. In this region, hydrogen maintains its molecular structure, but exists in liquid state due to immense pressure. The transition from liquid hydrogen to the gaseous atmosphere we observe is gradual, without a defined surface. Like Jupiter, Saturn emits significantly more energy than it receives from the Sun, about 2.5 times more to be precise. This extra energy comes from three main sources. The first is primordial heat remaining from the planet's formation 4.6 billion years ago. The second is the slow gravitational contraction of the planet, which continues today at a rate of about 0.04 inches or 1 millimeter per year. The third, and perhaps most significant for Saturn, is helium rain. Helium, heavier than hydrogen, slowly separates and precipitates towards the core through liquid hydrogen, releasing gravitational energy in the process. Saturn's magnetic field is about 600 times more powerful than Earth's, though significantly weaker than Jupiter's, about 20 times less intense. A unique characteristic of Saturn's magnetic field is that it's almost perfectly aligned with the planet's rotation axis. The inclination is only 0.06 degrees, the smallest of all planets in the solar system. This nearly perfect configuration has long puzzled scientists, since magnetic field generation models typically predict significant misalignment. The ring system, a cosmic masterpiece. Saturn's ring system is undoubtedly its most famous and spectacular feature, representing one of the most beautiful and complex phenomena in the solar system. These rings, which extend from the planet for a distance of over 248,548 miles, or 400,000 kilometers, more than the Earth-Moon distance, but have an average thickness of only 33 to 328 feet, or 10 to 100 meters, are composed mainly of 95 to 99% pure water ice particles, with traces of rocky material and organic compounds. The main system is subdivided into several principal rings, designated with alphabet letters in the order of their historical discovery. From the planet outward, we find the D ring, the innermost and most tenuous, followed by rings C, B, and A, the most visible and massive. Then the F ring, thin and dynamically complex. The G ring, extremely weak, and the E ring, the outermost and most extended, fed by Enceladus's geysers. The D ring is the innermost and most tenuous of the main system, extending from about 41,633 miles or 67,000 kilometers to 46,293 miles or 74,500 kilometers from Saturn's center. Composed of extremely fine dust particles, this ring is so thin it was only discovered by the Voyager probes in 1980. Particles in this ring are slowly spiraling towards Saturn due to atmospheric friction and electromagnetic effects. The C ring, also known as the Crepe ring due to its transparency, extends from 46,293 miles or 74,500 kilometers to 57,166 miles or 92,000 kilometers from the planet's center. With an average thickness of only 16 feet or 5 meters, it contains several notable structures, including the Colombo division and Maxwell division. A peculiar feature of the C ring are the spokes, radial dark structures that appear and disappear on hourly timescales. probably composed of electrically charged dust particles lifted from the ring's surface by the planet's magnetic field. The B ring is the most massive and opaque of the entire system, containing about 95% of the total ring mass. It extends from 57,166 miles, or 92,000 kilometers, to 73,015 miles, or 117,500 kilometers, from Saturn's center, and has a thickness varying from 16 to 49 feet, or 5 to 15 meters. Its optical density is so high that it's completely opaque to visible light. The B ring represents an extremely complex structure with thousands of concentric ringlets, density waves, and temporary structures created by gravitational resonances with Saturn's moons. The Cassini division, 2,983 miles or 4,800 kilometers wide, separates the B ring from the A ring and is the most prominent feature visible even from terrestrial telescopes. Contrary to popular belief, it's not completely empty but contains several thin ringlets and diffuse material. The division is maintained primarily by a 2-to-1 resonance with the moon Mimas, which removes particles from this region through accumulated gravitational perturbations over time. The A ring extends from 75,916 miles, or 122,200 kilometers, to 85,016 miles, or 136,800 kilometers, from Saturn's center. One of its most notable features is the Encke division, 202 miles or 325 kilometers wide, within which orbits the small moon Pan, 22 miles or 35 kilometers in diameter, 83,265 miles or 134,000 kilometers from Saturn. Pan acts as a shepherd moon, creating the division through its gravitational attraction and keeping the division's edges clean of debris. The F ring deserves special mention for its dynamic and complex nature. Located 87,122 miles or 140,180 kilometers from Saturn's center, this thin and relatively dense ring is shepherded by two small moons, Prometheus, 53 miles or 86 kilometers in diameter, 86,590 miles or 139,350 kilometers from Saturn, and Pandora, 50 miles or 81 kilometers in diameter, 88,049 miles or 141,700 kilometers from Saturn, which orbit respectively inside and outside the ring. Gravitational interactions with these moons create a dynamic environment where the ring continuously forms knots, braids, and temporary structures that change within hours or days. The E ring is the outermost and most extended of the Saturnian system, extending from about 111,847 miles or 180,000 kilometers to over 298,261 miles or 480,000 kilometers from the planet's center. It's also the thickest, with heights reaching 1,553 miles or 2,500 kilometers above and below the equatorial plane. The E-ring is continuously fed by the famous geysers of the moon Enceladus, 314 miles or 504 kilometers, 147,909 miles or 238,000 kilometers from Saturn, which eject water vapor and ice particles at sufficient velocities to escape the moon's gravity. Ring particles vary enormously in size, from microscopic dust grains to house-sized boulders. The size distribution approximately follows a power law, with smaller particles much more numerous than larger ones. These particles orbit Saturn following Kepler's laws, with those closer to the planet moving faster than those farther away, creating density waves and complex structures. One of the most surprising discoveries of the Cassini mission was the presence of temporary and dynamic structures in the rings. The spokes are electrostatic phenomena that seem to rotate together with the planet's magnetic field, rather than following normal Keplerian orbital laws. These spokes are more visible when Saturn is in certain positions relative to the Sun and show seasonal variations. Space exploration of Saturn. Saturn's close-up exploration has been a complex undertaking, given the enormous distance from Earth and the hostile environment surrounding the planet. The first probe to visit the gas giant was Pioneer 11 in September of 1979, which provided the first close-up images and confirmed the existence of the magnetic field. It was followed by Voyager 1 in November 1980 and Voyager 2 in August of 1981, which revolutionized our understanding of the Saturnian system by providing detailed images of the rings and discovering many of the minor moons. The Voyager probes revealed the structural complexity of the rings, discovered the first spokes, identified several new moons, and provided the first detailed measurements of Saturn's atmosphere and magnetic field. However, the real qualitative leap in Saturn's exploration came with the Cassini-Huygens mission, an ambitious collaboration between NASA, the ESA, the European Space Agency, and ASI, the Italian Space Agency. Launched in October of 1997, the Cassini-Huygens mission reached Saturn on July 1, 2004, after a journey of almost 7 years that included gravitational flybys of Venus twice, Earth, and Jupiter to accelerate towards the final destination. The Cassini probe became the first spacecraft to orbit Saturn, while the Huygens probe developed by ESA was destined to land on Titan's surface. On December 5, 2004, Huygens separated from Cassini and began its journey to Titan. On January 14, 2005, the probe entered the Moon's atmosphere, and after a descent of 2 hours and 28 minutes through the dense atmosphere, landed on the surface, becoming the first human-made object to land on a moon in the outer solar system. During its descent and in the following hours, Huygens transmitted extraordinary images and scientific data that revealed a world surprisingly similar to primordial Earth, with rivers, lakes, and plains shaped by liquid methane erosion. The mothership, Cassini, spent 13 years orbiting Saturn, completing 294 orbits and conducting in-depth studies of the planet, its rings, and its moons. The mission, initially planned to last 4 years, was extended multiple times thanks to the probe's excellent health and the extraordinary quality of scientific data collected. Cassini revolutionized our understanding of the Saturnian system, discovering geysers on Enceladus, hydrocarbon lakes on Triton, new moons, and complex ring structures. The mission's final months were dedicated to the grand finale orbits, 22 spectacular orbits that brought Cassini between the planet and its rings into a region never explored before. These final orbits provided unprecedented measurements of Saturn's upper atmosphere composition, internal ring structure, and the planet's gravitational field. The mission deliberately concluded on September 15, 2017, when Cassini was made to crash into Saturn's atmosphere to avoid possible contamination of potentially habitable moons in case of probe control loss. Saturn's moons, a miniature solar system. Saturn has 274 confirmed moons in its orbit, far more than any other planet in our solar system. In March of 2025, astronomers confirmed the discovery of 128 small moons around Saturn, adding to the already large moon count. These moons can be subdivided into different categories: large, regular moons that orbit in the planet's equatorial plane, small inner moons associated with the rings, and numerous groups of irregular moons that orbit at great distances with often eccentric and retrograde orbits. Titan, 3,200 miles or 5,149 kilometers in diameter, 729,235 miles or 1.2 million kilometers from Saturn, Saturn's largest moon and the second largest in the solar system after Jupiter's Ganymede, is a fascinating world representing one of the celestial bodies most similar to primordial Earth. Larger than Mercury, it possesses a dense atmosphere composed of 98.4% nitrogen and 1.6% methane, with traces of ethane, propane, acetylene, and other complex hydrocarbons. Surface atmospheric pressure is 1.45 times Earth's, making Titan the only satellite in the solar system with a substantial atmosphere. Titan's surface hosts a complete hydrological cycle similar to Earth's, but with liquid methane and ethane instead of water. Data from the Cassini-Huygens missions revealed rivers, lakes, and seas of liquid hydrocarbons, mainly concentrated in polar regions. The largest of these liquid bodies is Kraken Mare in the northern hemisphere, covering an area of about 154,441 square miles or 400,000 square kilometers, and potentially over 984 feet or 300 meters deep. Titan's climate presents pronounced seasons due to Saturn's inclination, with each season lasting about 7 Earth years. Beneath Titan's frozen crust, theoretical models suggest the presence of a subsurface ocean of liquid water, located 31 to 62 miles or 50 to 100 kilometers deep. This ocean could be up to 124 miles or 200 kilometers deep and contain more water than all Earth's oceans combined. The presence of dissolved ammonia could lower water's freezing point, keeping the ocean liquid despite low temperatures. Titan's complex organic chemistry makes it one of the most interesting places for astrobiology. Enceladus, 314 miles or 504 kilometers in diameter, 147,909 miles or 238,000 kilometers from Saturn. A small icy moon has become one of the most intriguing destinations for life research after Cassini discovered spectacular geysers of water vapor and ice particles erupting from its south polar region. These geysers, nicknamed tiger stripes because of the 4 parallel fractures from which they emanate, eject material at speeds up to 497 miles per hour or 800 kilometers per hour, reaching heights over 311 miles or 500 kilometers above the surface. Enceladus's geological activity is powered by tidal heating caused by orbital resonance with Dion and orbital eccentricity maintained by gravitational perturbations from other moons. Beneath Enceladus's icy crust hides a global ocean of salty liquid water about 6 miles or 10 kilometers deep. This ocean is in direct contact with the moon's rocky core, allowing chemical reactions that could produce molecular hydrogen and other compounds essential for life. Chemical analysis of the geysers revealed the presence of sodium chloride, carbonates, nanometric silica, and molecular hydrogen. Mimas, 246 miles or 396 kilometers in diameter, 115,280 miles or 185,520 kilometers from Saturn, is famous for its giant Herschel crater, which gives it an appearance similar to the Death Star from Star Wars. This monumental crater has a diameter of 81 miles or 130 kilometers and is 6 miles or 10 kilometers deep, with walls rising up to 3 miles or 5 kilometers above the bottom. The impact that created Herschel almost destroyed Mimas. A slightly more powerful collision would have completely fragmented the moon. Despite its small size, Mimas has a disproportionate gravitational influence on Saturn's ring system, being responsible for creating and maintaining the Cassini division through 2-to-1 orbital resonance. Iapetus, 913 miles or 1,469 kilometers in diameter, 2,212,889 miles or 3.56 million kilometers from Saturn, presents one of the most mysterious features in the Saturnian system: extreme two-tone coloration, with one hemisphere dark as coal, called Cassini Regio, and the other white as fresh snow. This dichotomy is so pronounced it's visible even from terrestrial telescopes. The dark material is probably composed of organic compounds derived from Saturn's outer irregular moons. Another unique feature of Iapetus is the equatorial ridge, a mountain chain up to 12 miles or 20 kilometers high that gives it a walnut-like appearance. Other major moons include Tethys, 662 miles or 1,066 kilometers in diameter, 183,095 miles or 294,670 kilometers from Saturn, characterized by the enormous Osidius crater and the imposing Ithaca chasma. Dion, 697 miles or 1,123 kilometers in diameter, 234,505 miles or 377,400 kilometers from Saturn, with its icy cliffs and bright streaks. And Rhea, 949 miles or 1,527 kilometers in diameter, 327,488 miles or 527,040 kilometers from Saturn, the second largest moon after Titan, with an ancient, heavily cratered surface. Numerous small moons act as ring shepherds. Pan, 22 miles or 35 kilometers in diameter, 83,265 miles or 134,000 kilometers from Saturn, orbits in the Enki division. Daphnis, 5 miles or 8 kilometers in diameter, 85,405 miles or 137,500 kilometers from Saturn, in the Keeler division, while Prometheus and Pandora maintain the complex structure of the F-ring. Future exploration prospects. Currently, there are no specific missions to Saturn in advanced development stages, but several ambitious concepts are under study. NASA's Dragonfly mission, approved for launch in 2027 with arrival at Titan in 2034, represents the next big step in Saturnian system exploration. This drone, powered by a radioisotope thermoelectric generator, will be able to fly in Titan's dense atmosphere for over 2 years, exploring various sites of astrobiological and geological interest. Future mission concepts include dedicated Enceladus orbiters that could fly through the geysers to directly sample the subsurface ocean, potentially detecting signs of microbial life. These missions would require advanced in situ biochemical analysis technologies and efficient propulsion systems for multiple orbital maneuvers in the Saturnian system. Sample return missions from Enceladus or Titan are considered the holy grail of Saturnian system exploration, but would require significant advances in space propulsion and sample preservation technologies for the long return journey. Telescopic observation continues to provide new information, especially through the James Webb Space Telescope, which can study Saturn's and its moon's atmospheres in infrared with unprecedented resolution. Conclusion: the eternal jewel. Saturn continues to represent one of the most fascinating natural laboratories in the solar system and a timeless symbol of cosmic beauty. With its majestic rings dancing in complex configurations, its moons hiding oceans and showing exotic geologies, and its atmosphere concealing storms with impossible geometries, the sixth planet from the Sun remains a monument to the extraordinary diversity and complexity of the universe. The discoveries of the Cassini mission have transformed our understanding of this world, revealing a dynamic and interconnected system where unique physical and chemical processes create phenomena that challenge our understanding and expand our scientific horizons. From hexagonal storms to icy geysers, from seasonal cycles lasting years to rings that continuously renew themselves, Saturn reminds us that the universe is full of wonders waiting to be discovered. As we look toward the future of space exploration, Saturn and its moons remain priority destinations for understanding not only the formation and evolution of our solar system, but also the possibilities of life beyond Earth. Its icy moons could host microbial ecosystems that would redefine our understanding of life in the universe, while its rings continue to serve as a natural laboratory for studying the processes governing planetary formation. In this golden giant floating in cosmic darkness, surrounded by its retinue of moons and glittering rings, we find not only an object of scientific study, but a reminder of the extraordinary beauty and complexity of the universe we call home. Saturn teaches us that even in the most remote and apparently inhospitable regions of the cosmos, nature can create structures of beauty and precision that surpasses any human artwork. History of Uranus, the coldest and strangest planet in the solar system. We continue our journey through the solar system. After exploring Saturn's hexagonal storms and its hidden oceans, it's time to venture even farther out, toward the icy regions, to encounter one of the most enigmatic and bizarre worlds, Uranus, the ice giant that defies every planetary convention. This planet isn't just a world of extreme climates and exotic compositions, but represents a true cosmic anomaly that continues to surprise astronomers. A giant that rotates completely on its side, like a ball rolling along its orbit, alternately showing its poles to the Sun for entire decades. A world where seasons last more than 20 Earth years, and where the atmosphere reaches temperatures so extreme that it becomes the coldest place in the solar system, even more frigid than Neptune, despite being much closer to the Sun. What do you say? Shall we pay it a little visit? Uranus is a planet that defies every expectation. The seventh world from the Sun, so distant that sunlight takes almost 3 hours to reach it. So cold that methane crystallizes in its upper atmosphere. So strange in its rotation that astronomers have had to redefine the concepts of North Pole and South Pole to describe it. With its characteristic blue-green coloration and its incredible axial tilt of 82 degrees, Uranus literally appears lying on its side as it orbits the Sun, creating a seasonal system unique in the solar system. But what makes this icy giant so special? With a diameter of 31,763 miles or 51,118 kilometers, about 4 times that of Earth, Uranus is the third largest planet in the solar system, but fourth by mass since its density of 1.27 grams per cubic centimeter or 79.3 pounds per cubic foot is significantly lower than that of Neptune, 1.64 grams per cubic centimeter or 102.4 pounds per square foot. It orbits at an average distance of 1.78 billion miles or 2.87 billion kilometers or 19.2 astronomical units from the Sun, completing one revolution in 84 Earth years, essentially the duration of an entire human lifetime. The ice giant rotates on its axis in 17 hours and 14 minutes, but here begins its strangeness. The rotation axis is tilted 82.2 degrees relative to the orbital plane, which means Uranus rotates practically on its side. This unique characteristic means that during the long Uranian year, each pole receives continuous sunlight for 42 Earth years, followed by 42 years of complete darkness. Surface gravity is slightly less than Earth's, 0.886 times. So a person weighing 154 pounds on Earth would weigh about 136 pounds on Uranus. The average temperature in the upper atmosphere is minus 371 degrees Fahrenheit or minus 224 degrees Celsius, making it paradoxically colder than Neptune, despite being closer to the Sun. This thermal enigma is due to the fact that Uranus emits much less internal heat compared to other gas giants, for reasons still not completely understood by planetary science. A new planet after millennia. The story of Uranus's discovery is as fascinating as the planet itself. Until March 13, 1781, humanity knew only 6 planets in the solar system, from Mercury to Saturn. That night, in the spa town of Bath, England, a German musician, naturalized as British, named William Herschel was conducting a methodical observation of the sky with a reflecting telescope of his own construction, equipped with a 6-inch or 15-centimeter diameter mirror. Herschel wasn't a professional astronomer, but an enthusiast who had developed extraordinary skill in telescope construction. Together with his sister Caroline, who would become the first paid woman astronomer in history, William spent nights observing double stars in an attempt to measure stellar parallaxes. That particular evening, while scanning the constellation Gemini, he noticed an unusual object that appeared slightly larger than surrounding stars and showed a clearly visible disk. Initially, Herschel thought he had discovered a comet. The object moved slowly against the stellar background, a characteristic that clearly distinguished it from fixed stars. But in the following weeks, when other astronomers calculated its orbit, it became evident that this was something much more significant: a new planet, the first to be discovered in modern times, and the first identified thanks to a telescope. Herschel's discovery not only doubled the known size of the solar system, but also demonstrated that worlds existed beyond the imagination of the ancients. As a reward for his discovery, King George III appointed Herschel court astronomer and granted him a pension that allowed him to dedicate himself completely to astronomy. Herschel initially proposed calling the new planet Georgium Sidus, or George's star, in honor of the sovereign, but eventually the name Uranus prevailed, suggested by German astronomer Johann Bode, maintaining the tradition of naming planets after figures from classical mythology. Composition and structure: a different giant. Uranus belongs to the category of ice giants. a distinction that separates it both from gas giants like Jupiter and Saturn and from the inner rocky planets. Its composition is dominated by materials that astronomers call ices, not in the sense of frozen water, but volatile substances like water, methane, and ammonia in supercritical phase, along with hydrogen and helium. Uranus's internal structure is organized into three main layers. At the center lies a small rocky core composed of silicates and iron-nickel, with a mass of about 0.55 Earth masses and a radius representing less than 20% of the planetary radius. This core is surrounded by a massive mantle of hot ices, mainly water, methane, and ammonia in fluid form, which constitutes most of the planet's mass, about 13.4 Earth masses. Everything is wrapped in a relatively thin atmosphere of hydrogen and helium that represents only about 0.5 Earth masses. What makes Uranus truly unique is its magnetic strangeness. The planet's magnetic field isn't aligned with the rotation axis as would be expected, but is tilted a full 58.6 degrees relative to it. Moreover, the center of the magnetic field is offset by about 1/3 of the planetary radius from the planet's geometric center. This bizarre configuration suggests that the magnetic field might be generated not in the deep core, but in the intermediate layers of the conductive ice mantle. Uranus's atmosphere is composed of 83% molecular hydrogen, 15% helium, and 2% methane, with traces of water vapor and ammonia. It's precisely the methane that gives the planet its characteristic blue-green coloration. This gas strongly absorbs red light while reflecting blue and green wavelengths. The presence of methane in the upper atmosphere was unexpected, given that at those temperatures, minus 371 degrees Fahrenheit or minus 224 degrees Celsius, it should be completely frozen. An extreme and mysterious climate. Uranus's climate is governed by its extraordinary axial tilt, which creates a seasonal system unique in the solar system. Unlike other planets where seasons are caused by varying distance from the Sun, on Uranus they depend entirely on which pole is facing our star. During Uranian summer, one pole receives direct and continuous sunlight for 42 Earth years, while the other remains in complete darkness. Then, the situation reverses for another 42 years. Despite this extreme configuration, Uranus shows surprisingly fast winds that can reach 560 miles per hour, or 900 kilometers per hour, among the fastest in the solar system. These winds blow mainly in the direction of the planet's rotation, but the mechanism that powers them remains mysterious, given that Uranus receives so little solar energy and generates very little internal heat. The Voyager 2 probe, which visited Uranus in 1986, observed an apparently calm atmosphere with very few visible features. However, more recent observations from the Hubble telescope have revealed that Uranus can develop dynamic storm systems, especially when approaching equinoxes, moments when both hemispheres receive solar illumination. A particular mystery concerns Uranus's atmospheric temperature. Despite being closer to the Sun than Neptune, Uranus is systematically colder. While Neptune emits 2.6 times more energy than it receives from the Sun, Uranus emits almost the same amount it receives, suggesting a much less thermally active interior. Theories range from different internal composition to consequences of the impact that might have caused its anomalous rotation. Hey guys, just a moment before we continue. Be sure to join the Insane Curiosity channel. Click on the bell. You'll help us to make products of even higher quality. A complex system of rings and moons. Uranus possesses a ring system discovered only in 1977, when astronomers aboard the Kuiper Airborne Observatory observed the planet occulting a distant star. To their surprise, the stellar light dimmed several times before and after the main occultation, revealing the presence of thin, dark rings. Uranus's ring system is composed of 13 confirmed rings, very different from Saturn's spectacular ones. Uranus's rings are extremely dark, reflecting only 2% of incident light, and are probably composed of organic material altered by radiation. The most prominent is the Epsilon ring, about 62 miles or 100 kilometers wide, with particles ranging from fine dust to boulders several yards across. Uranus's 28 known moons are equally unique in the solar system. Unlike moons of other planets, which take names from Greek or Roman mythology, those of Uranus are named after characters from the works of William Shakespeare and Alexander Pope, earning them the nickname literary moons. This tradition began with John Herschel, son of Uranus's discoverer, who in 1852 named the first 4 known moons. Besides the 5 major moons, Uranus possesses 23 minor moons discovered mainly by the Hubble telescope and advanced ground-based observations. 10 of these were identified by Voyager 2 in 1986. Cordelia, 25 miles or 40 kilometers in diameter, Ophelia, 27 miles or 43 kilometers, Bianca, 32 miles, 51 kilometers, Chrysidia, 50 miles or 80 kilometers, Desdemona, 40 miles or 64 kilometers, Juliet, 58 miles, 94 kilometers, Portia, 84 miles or 135 kilometers, Rosalind, 45 miles or 72 kilometers, Belinda, 56 miles or 90 kilometers, and Puck, 101 miles or 162 kilometers. These small moons orbit between the rings and major moons, some acting as shepherds to maintain ring structure. The outer irregular moons discovered between 1997 and 2003 include Caliban, Sycorax, Prospero, Setebos, Stefano, Trinculo, Francisco, Margaret, and Ferdinand. These moons, with diameters between 5 and 93 miles or 8 and 150 kilometers, orbit at enormous distances, 2.5 to 12.4 million miles or 4 to 20 million kilometers, on retrograde and highly eccentric trajectories, suggesting they are asteroids captured by Uranus's gravity. The most recent discovery dates to November 2023, bringing the total to 28 confirmed moons. Miranda, 294 miles or 472 kilometers in diameter, 80,654 miles or 129,800 kilometers from Uranus, the smallest of the major moons, is perhaps the most fascinating and mysterious. Its surface presents a patchwork appearance with terrains of different ages juxtaposed in apparent random ways, a unique characteristic in the solar system. Canyons 12 miles or 20 kilometers deep, 12 times deeper than the Grand Canyon, carved through its icy surface, while oval structures called coronae indicate complex geological processes. Its density of 1.2 grams per cubic centimeter or 74.9 pounds per cubic foot suggests an ice-rich composition. Some theories propose that Miranda was fragmented by catastrophic impacts and then reassembled under its own gravity, explaining its fragmentary appearance. Ariel, 719 miles or 1,158 kilometers in diameter, 118,000 miles or 191,200 kilometers from Uranus, is the brightest of the Uranian moons, with an albedo of 23%. Its relatively young surface shows few large craters, but many small ones, indicating recent geological renewal events. Intersecting valleys and scarps across the surface, some partially filled with material that may have upwelled from the interior. Its density of 1.67 grams per cubic centimeter, or 104.2 pounds per cubic foot, indicates a mixed composition of ice and rock in nearly equal proportions. Umbriel, 726 miles or 1,169 kilometers in diameter, 165,300 miles or 266,000 kilometers from Uranus, is the darkest of the major moons, reflecting only 16% of incident light, blacker than asphalt. Its ancient surface is densely cratered, similar to lunar highlands. A mysterious bright ring, 87 miles or 140 kilometers in diameter, stands out on its dark surface, whose origin remains unexplained. Its density of 1.4 grams per cubic centimeter, or 87.4 pounds per cubic foot, suggests a balanced composition of ice and rock. Titania, 981 miles or 1,578 kilometers in diameter, 271,100 miles or 436,300 kilometers from Uranus, the largest moon in the system, presents varied terrain with craters, canyons, and smooth plains. Valleys up to 62 miles or 100 kilometers deep carve the surface, testifying to past tectonic activity. Its density of 1.71 grams per cubic centimeter, or 106.8 pounds per cubic foot, is the highest among Uranian moons, indicating greater rocky content. Recent models suggest Titania might harbor a residual ocean up to 31 miles or 50 kilometers deep beneath its icy crust. Oberon, 946 miles or 1,523 kilometers in diameter, 362,600 miles or 583,500 kilometers from Uranus, the outermost of the major moons, shows an ancient, densely cratered surface, reminiscent of Saturn's moon Rhea. Several craters display bright rays and central material, indicating relatively recent impacts. Its density of 1.63 grams per cubic centimeter, or 101.8 pounds per cubic foot, is similar to Titania's. Like Titania, it might hide a subsurface ocean maintained by thermal metamorphism processes. Visited by a single probe, Voyager 2. Uranus's close-up exploration has been entrusted exclusively to the Voyager 2 probe, which reached the planet on January 24, 1986, after an 8.5-year journey. This encounter represents one of the triumphs of space engineering. Voyager 2 had to be reprogrammed to adapt to Uranus's anomalous rotation and unusual magnetic fields. During the close flyby, passing just 50,600 miles or 81,500 kilometers from the cloud tops, Voyager 2 transmitted over 7,000 images and an enormous amount of scientific data. The probe discovered 10 new moons, 2 new rings, and provided the first detailed measurements of Uranus's magnetic field. The images revealed an apparently monotonous world with an atmosphere almost devoid of distinctive features, a stark contrast to Jupiter's turbulent storms and Saturn's colored bands. However, Voyager 2's data has continued to reveal secrets for decades. In 2020, a reanalysis of magnetic data identified a gigantic magnetic bubble, plasmoid, that had detached from Uranus during the probe's passage, suggesting much more dynamic magnetospheric processes than initially understood. Voyager 2's scientific legacy has also highlighted how little we still know about Uranus. The probe observed the planet during southern solstice, when one pole was facing almost directly toward the Sun. This means we've never closely observed Uranus's atmosphere during other seasons, leaving many questions about its seasonal atmospheric dynamics. After Galileo at Jupiter, Cassini at Saturn, and Juno continuing to study Jupiter, ice giants remain the last class of solar system planets without a dedicated orbiting explorer. International efforts to realize such a mission are intense and coordinated. The European Space Agency has included ice giant exploration in its Strategic Voyage 2050 program, while NASA has identified a Uranus mission as an absolute priority for the next decade. Advanced mission concepts include combinations of orbiters, atmospheric probes, and even landers on icy moons. Unsolved mysteries and future prospects. Uranus remains one of the least understood planets in the solar system, with more questions than answers. The origin of its anomalous rotation is still debated. A gigantic impact during planetary formation, chaotic orbital migration, or perhaps a combination of catastrophic events. New theories suggest that instead of a single massive impact, a series of smaller collisions with moon-sized objects might have gradually tipped the planet over. Its eccentric magnetic field suggests internal processes fundamentally different from those of other giants. The lack of internal heat. Uranus emits only 1.06 times the energy it receives from the Sun, much less than other gas giants, challenges planetary evolution models. This energy deficit might be considered to the great impact that caused its anomalous rotation, possibly dispersing the planet's primordial heat into space. Even its apparently calm atmosphere might hide complex dynamics that we only partially observe from Earth. Recent observations from the James Webb Telescope have revealed unprecedented details of rings and seasonal storms, suggesting Uranus is much more active than Voyager 2 observed during its brief encounter. The most recent studies suggest that Uranus's major moons might harbor residual oceans beneath their icy surfaces. Titania and Oberon might maintain liquid layers up to 31 miles or 50 kilometers thick, thanks to late thermal metamorphism, while Ariel and Umbriel might have thinner oceans, less than 19 miles or 30 kilometers. These oceans, if they exist, might be hypersaline and therefore detectable through induced magnetic fields, opening new possibilities for astrobiology. Uranus as archetype of extrasolar worlds. Uranus and Neptune represent much more than simple curiosities in our solar system. They are archetypes of the most common class of planets in the universe. Observations from the Kuiper Space Telescope have revealed that planets with masses and sizes intermediate between Earth and Neptune, the so-called super-Earths and mini-Neptunes, are the most abundant among known exoplanets. These worlds, with radii between 1.8 and 4.0 Earth radii, represent a planetary category completely absent from our solar system but dominant in the galaxy. Most orbit very close to their host stars, completing an orbit in less than 100 days, creating extreme environmental conditions that might be common in the universe. Studying Uranus and Neptune therefore provides us with a natural laboratory for understanding physical processes that might be fundamental to billions of worlds throughout the Milky Way. The unique composition of ice giants, dominated by volatile compounds like water, methane, and ammonia rather than hydrogen and helium, represents a key to understanding how these intermediate worlds form. Current planetary formation models struggle to explain how Uranus and Neptune could have accreted their masses in their present position, where the protoplanetary disk was too rarefied and formation timescales too long. Three main scenarios compete to explain ice giant formation. Core accretion in their current position, unlikely given the low density of the outer disk. Formation closer to the Sun followed by outward migration, supported by the Nice model, and direct gravitational instability of the protoplanetary disk that would create massive protoplanets in relatively short times. The last scenario is particularly intriguing because it could explain rapid ice giant formation even in short-lived protoplanetary disks, which exist for only a few million years. Regions of slightly higher density in the disk could collapse directly into protoplanets with planetary density and timescales of thousands of years, much faster than the 100,000 to 1 million years required by traditional core accretion. To conclude, Uranus reminds us that the universe is full of surprises that challenge our expectations. This giant that rotates on its side with its frigid atmosphere and magnetic mysteries represents a fundamental chapter in solar system history. Its discovery revolutionized our understanding of cosmic vastness, while its unique characteristics continue to challenge our planetary models. In this distant world where seasons last decades and winds blow at supersonic speeds through an atmosphere of frozen methane, we find a reminder of incredible planetary diversity. Uranus teaches us that even in the most remote and apparently inhospitable places in the cosmos, nature can create phenomena of complexity and beauty that surpasses our imagination. Okay, folks, that's all for Uranus. Our journey will continue with Neptune, the last of the major planets, a world of devastating winds and icy moons that will complete our tour of the most remote domains of the solar system. History of Neptune, the last guardian of the solar system. Here we are at the final stop of our extraordinary journey through the most extreme frontiers of the solar system. After exploring Uranus's magnetic anomalies and its upside-down rotation, we're heading toward the ultimate planetary frontier, Neptune, the eighth and most distant of the major planets. A world of titanic storms and profound mysteries that reigns supreme in the frigid cosmic periphery. This ice giant doesn't simply represent the final chapter of our exploration, but embodies the triumph of mathematics over chance. The first planet in history discovered not through direct observation, but through theoretical calculations. A world where winds reach supersonic speeds that defy all physical logic. Where a great dark spot appears and disappears like an atmospheric phantom. and where a captured moon dances an orbital dance backwards, challenging gravitational conventions. Are you ready for this final epic journey to the edges of our planetary system? Neptune dominates the most remote regions of the solar system from an average distance of 4.5 billion kilometers, or 2.8 billion miles, or 30.1 astronomical units from the Sun. At this incredible distance, sunlight takes more than 4 hours to reach this frozen world, where illumination is 1,000 times weaker than what we experience on Earth. Yet, as we're about to see, despite this energy poverty, Neptune turns out to be the most dynamic and meteorologically active planet in the entire solar system. With a diameter of 49,528 kilometers or 30,775 miles, Neptune is slightly smaller than Uranus at 50,724 kilometers, but its higher density, 1.64 grams per cubic centimeter versus 1.27, gives it a mass equal to 17.5 times that of Earth compared to Uranus's at 14.5. Neptune's orbital period extends for 164.8 Earth years, a time so long that since its discovery in 1846, it has completed barely one complete revolution around the Sun in 2011. Rotation on its own axis takes 16 hours and 6 minutes, slightly faster than Uranus. Unlike its predecessor, Neptune's rotational axis has a normal inclination of 28.3 degrees, similar to Earth's, creating conventional seasons that last over 40 Earth years each. Despite receiving only 1,000th of the solar energy that reaches Earth, Neptune maintains atmospheric temperatures of minus 218 degrees Celsius or minus 360 degrees Fahrenheit, paradoxically warmer than those of Uranus despite being farther from the Sun. This thermal paradox is explained by the fact that Neptune radiates 2.6 times more energy than it receives from our star, testifying to an interior still active from geological and thermal standpoints. A planet found through celestial mechanics. The story of Neptune's discovery represents one of the most fascinating chapters in modern astronomy, demonstrating the predictive power of mathematics and theoretical physics. It all began with a supposed orbital anomaly. After Uranus's discovery in 1781, astronomers noticed that the planet didn't follow exactly the orbit predicted by Newton's laws. These orbital perturbations suggested the presence of another massive body gravitationally influencing Uranus's movement. In 1843, young English mathematician John Couch Adams, then a student at Cambridge, undertook the ambitious challenge of calculating the unknown planet's position, based exclusively on the observed perturbations. His calculations, completed in 1845, identified a specific region of the sky where the mysterious eighth planet should be located. However, the British astronomical establishment showed little interest in Adams' predictions, not following up on his request for direct observations. Meanwhile, in France, astronomer Urbain Le Verrier was conducting independent calculations, arriving at surprisingly similar conclusions. Le Verrier managed to convince German astronomer Johann Galle at the Berlin Observatory to search for the planet in the predicted position. On the evening of September 23, 1846, Galle and his assistant Heinrich d'Arrest pointed their telescope toward the constellation Aquarius and, comparing observations with detailed star maps, identified an object that didn't appear on the charts, located less than 1 degree from the theoretically calculated position. This discovery sparked an international controversy over scientific priority, with the British and French claiming credit. Today, Adams and Le Verrier are recognized as co-discoverers of Neptune, celebrating the triumph of the scientific method and international collaboration. The name Neptune, suggested by Le Verrier himself in honor of the Roman god of the seas, was universally accepted, maintaining the mythological tradition in planetary nomenclature. Anatomy of an ice giant. Neptune's atmosphere, relatively thin compared to the planet's size, is composed of 83% molecular hydrogen, 15% helium, 1% methane, and traces of deuterated hydrogen, ethane, and water vapor. Like Uranus, it's the atmospheric methane that gives Neptune its characteristic deep blue coloration, absorbing red light and reflecting blue wavelengths. However, Neptune's blue appears more intense and vivid than that of Uranus, suggesting the presence of an additional component not yet identified that amplifies the selective light absorption. The atmosphere hosts the most extreme and dynamic meteorological phenomena in the solar system, a paradox considering its distance from the Sun and the consequent scarcity of available external energy. Neptune's winds reach speeds that defy conventional physical understanding, up to 2,100 kilometers per hour or 1,300 miles per hour, making them the fastest ever recorded on any planet in the solar system, even exceeding the speed of sound on Neptune. These supersonic winds blow mainly in a retrograde direction, opposite to planetary rotation, a phenomenon that further amplifies the mystery of their origin. The energy source of these winds remains one of the great enigmas of planetary meteorology. While terrestrial winds derive from differential solar energy and Jupiter's are powered by the planet's internal heat, Neptune combines both energy sources uniquely, with internal heat dominating despite the presence of a weak solar gradient. Neptune's most famous atmospheric feature was the Great Dark Spot, an Earth-sized storm system observed by the Voyager 2 probe in 1989. This gigantic anticyclonic storm, similar in structure to Jupiter's Great Red Spot, had peripheral winds of 2,400 kilometers per hour and moved westward at 1,200 kilometers per hour relative to surrounding clouds. However, when the Hubble telescope observed Neptune in 1994, the Great Dark Spot had completely disappeared, replaced by a new storm in the northern hemisphere. This behavior highlights the dynamic and transitory nature of Neptunian storms, which form, evolve, and dissipate on much shorter timescales compared to the stable meteorological systems of Jupiter and Saturn. Hubble observations have documented the appearance and disappearance of at least 6 large dark spots over 3 decades, suggesting these systems have typical lifespans of 2 to 6 Earth years. Beyond the great storms, Neptune's atmosphere shows subtle horizontal bands, bright circular clouds that change on hourly timescales, and southern cloud structures that appear linked to seasonal changes. The brightest clouds are composed of methane crystals forming in the upper atmospheric layers, while deeper formations might contain ammonium hydroxide and hydrogen sulfide. This blue giant's magnetic field also presents unique and puzzling characteristics. Like Uranus, it's not aligned with the planetary rotation axis, but is tilted 47 degrees relative to it. The magnetic field center is also offset by 0.55 planetary radii from the planet's geometric center, an even more extreme characteristic than that observed on Uranus. This configuration suggests the magnetic field is generated in intermediate layers of the conductive mantle rather than the deep core, supporting models proposing distributed dynamo mechanisms in these exotic worlds. The internal structure also reveals a complex architecture that clearly distinguishes it from the gas giants of the inner solar system. At the planet's center extends a rocky core composed mainly of silicates, iron, and nickel, with an estimated mass between 0.55 and 1.0 Earth masses, and temperatures that could reach 5,100 degrees Celsius, comparable to the solar surface. This core is surrounded by a massive mantle of hot ices, mainly water, methane, and ammonia in supercritical phase, which constitutes most of the planetary mass. These materials, compressed at enormous pressures and heated by planetary depths, behave like electrically conductive fluids, contributing to the generation of a strong magnetic field. The mantle extends for about 80% of the planetary radius and contains approximately 10 to 15 Earth masses of material. Only Voyager 2 arrived here too. Direct exploration of Neptune, like that of Uranus, remains entrusted exclusively to the Voyager 2 probe, which completed its grand tour of the outer planets with a magnificent flyby of the Neptunian system on August 25, 1989. This encounter represented the culmination of a 12-year mission and marked the final stage of initial exploration of all major planets in the classical solar system. Voyager 2 approached Neptune to within 4,950 kilometers of the cloud tops, the closest distance reached by the probe during all its planetary encounters. During this crucial flyby, the probe transmitted over 9,000 images and collected scientific data that revolutionized our understanding of this remote world. The discovery of the Great Dark Spot, supersonic winds, Triton's geysers, and 6 new moons transformed Neptune from a telescopic point of light into a complex and dynamic world. For the future, several space agencies are developing mission concepts for the ice giants. NASA has identified a mission to the Uranus and Neptune systems as maximum scientific priority for the next decade, while the European Space Agency includes ice giant exploration in its long-term strategic program, Voyage 2050. A unique moon system, the realm of Triton. Neptune's satellite system is distinctly different from those of other giants due to the overwhelming dominance of a single giant moon, Triton. This frozen world, with a diameter of 2,704 kilometers or 1,680 miles, contains over 99.5% of the mass of the entire Neptunian satellite system, an unprecedented mass concentration among the outer planets. Triton orbits Neptune at a distance of 354,800 kilometers in a retrograde direction, completing a revolution in 5.88 Earth days in perfect gravitational synchrony that keeps the same face always turned towards the planet. The retrograde orbit is highly unusual for a moon of such size and strongly suggests that Triton is a captured object, probably a large Kuiper Belt asteroid that was trapped by Neptune's gravity during a close encounter billions of years ago. Triton's surface presents unique characteristics in the solar system, with surface temperatures of minus 235 degrees Celsius or minus 391 degrees Fahrenheit. It's one of the coldest places in the solar system, yet shows clear evidence of recent geological activity. Its young surface, with very few impact craters, is dominated by icy plains, rough terrain called cantaloupe terrain for its resemblance to melon rind, and fracture systems indicating active tectonic processes. The most surprising discovery was that of Triton's nitrogen geysers, first observed by Voyager 2. These gas jets reach heights of 8 kilometers above the surface and are carried by winds for over 150 kilometers, depositing dark material in streaks that stain the bright ice. The mechanism powering these geysers remains debated. It could be seasonal heating of nitrogen deposits beneath the surface, or endogenous processes related to tidal heating. Triton's atmosphere, though tenuous, is composed mainly of nitrogen with traces of methane and carbon monoxide. Atmospheric pressure is about 70,000 times weaker than Earth's, but sufficient to support clouds and haze in the ionosphere. This atmosphere is in dynamic equilibrium with surface deposits of frozen nitrogen, which sublimate and recondense following seasonal cycles lasting decades. Neptune's other moons pale in comparison to Triton. Nereid, the second largest moon with a 340-kilometer diameter, follows an extremely eccentric orbit that takes it from 1.4 to 9.6 million kilometers from the planet. This unusual orbit could be the result of gravitational perturbation caused by Triton's capture, which would have disrupted Neptune's original satellite system. The minor inner moons, Naiad, Thalassa, Despina, Galatea, Larissa, and Proteus, are small irregular bodies with diameters between 54 and 420 kilometers that orbit among Neptune's rings. These moons are probably fragments of the original satellite system, destroyed and reformed after Triton's capture. Proteus, the largest of these inner moons, has a distinction of being the largest celestial body that hasn't assumed a spherical shape, remaining notably irregular despite its considerable size. Thin and dynamic rings. Neptune's ring system, discovered in 1984 through stellar occultation observations, comprises 5 main rings named after astronomers involved in the planet's discovery: Gaul, Leverrier, Lassell, Arago, and Adams. These rings are notably different from Saturn's spectacular ones, being extremely dark, thin, and variable in density. The Adam's ring, the outermost and most interesting, presents a unique characteristic in the solar system: bright arcs concentrated in specific centers of the ring rather than a uniform distribution of material. These arcs, named Liberté, Égalité, Fraternité, and Courage, maintain their structure thanks to gravitational resonance with the moon Galatea, which confines ring material to specific regions through complex gravitational interactions. Neptune's rings are composed of dark organic particles that reflect only 2 to 3% of incident light, similar in comparison to materials found in C-type asteroids and Kuiper Belt objects. Their age is estimated at hundreds of millions of years, relatively young on geological scales, suggesting they're products of small moon fragmentation caused by meteoritic impacts or orbital instabilities. The variability observed in Neptune's rings, documented by Hubble telescope and Very Large Telescope observations, indicates these systems are dynamic and in continuous evolution. Some ring sectors seem to appear and disappear on yearly timescales, while others show brightness variations that could be linked to seasonal changes in solar illumination. Neptune and the universe of exoplanets. Neptune's importance transcends our solar system's boundaries, extending to the formation of extrasolar planets. Ice giants, as we saw with Uranus, represent the archetypes of a dominant planetary class in the observable universe. Subneptunes, or super-Earths, worlds with intermediate masses between Earth and Neptune that constitute the majority of known exoplanets. Kepler Space Telescope observations have revealed that planets with radii between 1.8 and 4.0 Earth radii are the most common in the galaxy, despite this category being completely absent in our solar system between Earth and Neptune. Many of these exoplanets orbit very close to their parent stars, completing orbits in days or weeks and experiencing extreme environmental conditions that could nonetheless be representative of billions of similar worlds. Neptune's composition and internal structure provide fundamental models for understanding these distant worlds. The transition between planets dominated by rock and metals, like Earth, and those dominated by volatile elements, like Neptune, might occur around 3 to 4 Earth radii, defining a critical frontier in planetary evolution that separates super-Earths from mini-Neptunes. Ice giant formation processes remain debated, with direct implications for understanding exoplanets. If Neptune formed through rocky core accretion followed by volatile capture, this process should be common in other planetary systems too. If instead it formed through direct gravitational instability of the protoplanetary disk, formation times would be much shorter, allowing ice giant formation even in short-duration protoplanetary disks. Neptunian-style exoplanet atmospheres show extraordinary diversity in spectroscopic observations. Some retain dense atmospheres rich in hydrogen and helium, while others seem to have completely lost their primordial gaseous envelope, leaving exposed rocky cores resembling super-Earths. Neptune represents an intermediate case that could help understand atmospheric loss processes and long-term planetary evolution. Final reflections. The last frontier. As we conclude this journey through the solar system's frontiers, from scorching Mercury to Neptune's icy depths, we carry with us the awareness that every world visited has contributed a unique chapter to the great story of planetary evolution. Neptune, the last guardian of our classical solar system, greets us from its cold cosmic distances, and its deep blue shines like a distant beacon, keeper of secrets awaiting future generations of space explorers. All right, guys, keep following us for more extraordinary journeys through the mysteries of the cosmos.